Hey, good morning, everybody. Thanks for getting up so early on a Sunday for the tutorials. I think it'll be worth your time. I think there's two very good tutorials today. The first one is modern system interconnects, and if we can pull up the slides on the main screen, that would be great. So we've got three speakers for this first tutorial, covering three different subjects. The first part will be based on describing the HyperTransport protocol and its future extensions, and that will be delivered by José Duato as a representative of the HyperTransport Consortium. If we could pull up the slides on the main screen, that would be great. Thank you. The second one will be based on a description of Intel's relatively recently announced QuickPath interconnect. Bob Safranek from Intel will be giving that part. And then finally, we wanted to give everyone an update on what's going on with PCI Express. So Jasmin Ajanovic from Intel will be covering that for us today. So here's the outline of what we're going to go through. Again, my name is Chuck Moore. I'm a corporate fellow at AMD, specialize in microprocessors and system design. One of the things I've noticed over the past couple of years is the increasing importance of these kind of interconnects for building the kind of systems we need to build, even in the commodity space. So this is a very, very relevant topic for the industry and for me personally. Each speaker will go for about 45 minutes. There'll be about 5 minutes of kind of clarifying questions after their presentation. We do have a break, as Keith said. It'll be more like 15 minutes, 20 minutes to give people a chance to actually get something to eat and say hello to friends. And then at the end, assuming we still have time, we're going to try a panel-style Q&A for about a half hour, just so that you can ask some more open-ended questions and get opinions from the three speakers. So just as an intro to all of this, you know, the PC system architecture is growing up fundamentally. It's no longer just a self-contained set of single processors, of course. We've gone from relatively small SMPs to moderate size, now to very large SMPs are starting to develop in the market today and in years to come. And in order to do that, of course, we have to connect up multiple sockets. And within each socket, of course, there's many processors within that, and that's the trick for getting to the large SMPs. Now, as we get to large SMPs, we also, in some cases, feel the need to virtualize them back down, which is kind of a funny, ironic trend, but it's unmistakable in the industry. So today, we offer support for virtualizing the CPU, of course, in many of the designs out there, but in the future, now and in the future, it'll be important to also virtualize I/O and even networking. So these bus standards, these interconnect standards, have to sort of take some of that into account. So I think you'll see shades of that coming out in the discussion. Of course, high bandwidth, coherence, and high memory bandwidth, coherence, and I/O subsystems are required. As you have more and more CPUs brought into a small area, you're really obligated to increase the amount of data supplied to them. So this puts pressure on this part of the design as well. So in order to achieve that reasonable system level balance, the interconnect has to ratchet up at a rate commensurate with the number of CPUs. So as a result, of course, there are these implications on interconnects. They're no longer, you know, multi-drop shared buses, in case you haven't been watching. They're more packet and switch-based interconnects. You know, these run at much, much faster rates. They tend to be point-to-point interfaces to lower the capacitance to allow for these higher speeds. And they tend to be layered structures with SerDes-based physical layers. So I've provided a little picture here that shows, you know, some of the layering that occurs before you actually get to the data. And it varies depending on the protocol. So in each of the speakers' presentations, you'll see a slight variant of this kind of a diagram. Also, reliability becomes incredibly important because you don't want a single device failure to block the system. So you've got to be able to deal with that. And in theory, these interconnects should support alternate paths, although not all system topologies offer that today. they'll continue to grow in importance. As I made the point already, SMP scalability is critical, and in order to get that, you have to have a balance with I/O and memory and the way these things talk to each other. The internode messaging and sharing, you know, as you put down multiple SMP nodes, you want them to be able to communicate effectively together. Of course, one technique for doing that is RDMA, but now there's some requirements on the interconnect between the nodes in order to support these kind of memory-based communications, and also the synchronization requirements between them. The other thing that's going on, of course, is, you know, as we shake out of this recession funk, I think we're going to see a resurgence in the investments towards modernized data centers, even more so than we had in the past. So there's going to be new requirements on them in terms of scalability and reliability and really taking advantage of commodity electronics. So again, these interconnects play a very fundamental role in the architecture of the data center, or they will in the future. And then, not to be left out, of course, down in the wireless space, in the embedded space, the wireless protocols for interconnect and I/O to the broader network are increasingly important. We're not going to be covering that in this tutorial. I just didn't want to leave it out from my intro. And in fact, here is a list of some of the key I/O and interconnect technologies. I break them down into memory transfer and coherence protocols, I/O connections, data center connections, and peripheral device connections. In reality, in this tutorial, we're going to be hitting these three. You know, trying to cover all of these in one morning session would be just too much, and we thought that these would be of the broadest interest, at least for today. So with that, that's my intro, and next what I want to do is introduce our first speaker, which is José Duato. José is a professor at Technical University of Valencia, Spain. He's the author of numerous papers and book chapters out there. But from an industry perspective, he's contributed to technology and supercomputers like the IBM Blue Gene L, the Cray T3E, uniprocessors like the Alpha 21-364, and switches like the Sun Magnum switch. He's also a spokesman for the Advanced Technology Group at the HyperTransport Consortium, and he's sort of representing that role here today. So, José?
Thank you, Chuck, for the introduction. Good morning, ladies and gentlemen. Well, I'm going to talk about the HyperTransport technology. And in presenting this technology, I would like to mention that in addition to myself, we also have here Brian Holden, Vice President and Chair of the Technical Working Group, and Mario Cavalli, who is the General Manager of the HyperTransport Consortium, who will be happy to ask questions if they are too specific in those respects as well. So, going with the presentation, this is the set of topics that I would like to cover today. And first I would like to start by talking about the scope and design goals, and in doing so, I will define a bit better what's the role of HyperTransport in this landscape that Chuck previously defined. And then I will go into more details about HyperTransport technology, covering it in a structured way, so that I will start by talking about the host interface, how the host devices, either processors or peripheral devices, interface with each other, and then how to interconnect a single device to a host, multiple devices to a host, and finally multiple hosts among them. Then I will talk about something that's closely related to the interconnects, which is the cache coherence protocol, because this kind of technology is basically defined to support interconnection between processors. So we have to take care about how to handle these. And then, although this technology was initially defined to interconnect devices within a single motherboard, now it has expanded to support interconnection beyond the motherboard. So we'll also take a quick look at how this technology can be used to extend connections beyond a single motherboard, and what's new in the latest version of this technology, which is 83. Then very quickly I will introduce some commercial aspects, but very quickly I will basically go over the slides. So what's the scope of this technology? Basically, HyperTransport technology was designed as a replacement, high-performance replacement for the processor front-side bus. And take into account that point-to-point links are much faster than multi-drop shared buses, basically because the capacitance, the parasitic capacitance is much lower, and therefore speeds can be much higher. In doing so, when we need to interconnect multiple processors among them, the basic goal is not just to interconnect the processors, but to allow a processor and all the cores within it to access remote memory and be able to do so in a way that's almost as fast as when accessing the local memory, and also to be able to access peripheral devices. So the goal was to design a system area network supporting cache coherent shared memory multiprocessors and I/O devices. Something that's kind of almost unique in HyperTransport technology, that's, well, now it's no longer the case, but it was when it was initially designed, is that it was a processor native technology. It was not implemented in external silicon, but instead it was implemented on the processor chip itself, and therefore it provided support for a much better integrated access to different devices. It was integrated in processor architectures, not only in AMD processors, but also in other set of devices currently in the market. So what were the design goals for HyperTransport? Basically, it intended to be a very low latency, high bandwidth interconnect. But not only this, because there were other components or other systems in the market that already deliver low latency and high bandwidth. It intended to do so at very low cost. So it intended to be cost effective and reliable so that we could interconnect processors, memory, peripheral devices at very low cost in a very efficient manner. And as Chuck mentioned before, the idea was to support the shared memory programming model, so it's an SMP programming model. And as I mentioned before, the idea was to have a unified interface so that processors could access local memory as well as remote memory in exactly the same way. In order to do so, take into account that different manufacturers were going to use the processors in different ways, it was necessary to provide support for self-configuring topologies and link speeds so that we could interconnect different devices together and they could adapt themselves to each other by configuring these things at boot time in an automatic way. And over time, there have been several generations of HyperTransport. We are currently at HyperTransport 3.1. And there were some additional goals for this latest version. Basically, we wanted, of course, to increase bandwidth and reliability, but we added some additional features that allow this technology to go beyond a single motherboard and to interconnect a larger number of devices. For instance, link splitting, dynamic power management, AC mode, and hot plugging. I'm not going to detail them now. I will detail them later. So typical server architecture today basically consists of multiple motherboards, each of them having multiple processor sockets with DRAM slots and also some peripheral devices and controllers. And basically, those processors allow access to local memory as well as remote memory, and also they allow access to those multiple peripheral interconnects in a simple, relatively simple way and with low latency. And this is where HyperTransport fits very well, because it allows the coherent access of local as well as remote memory, as well as the access to all of those peripheral devices, as well as bridging to other technologies like PCI Express or USB or serial ATA or whatever. So now I'm going to detail a bit more the internals of HyperTransport technology, and I will start by talking about the interface with the host. This is a typical processor chip. Well, I didn't include more cores. I could have included many more, but basically, in order not to obscure the details, I just included a couple of them so that you could see that in a processor chip with multiple cores, Those processors usually access memory by issuing load or write, load or store instructions, and in doing so, they first try to find the data in the L1 or L2 or L3 caches, but if they don't find it there, then they have to access memory. So instead of directly attaching the DRAM controller to those cores or to the cache controller, in those modern chips, the idea is that there is a unified system request queue or system request interface that gathers all of those requests from different cores and channels them through a single interface so that they can later reach a DRAM controller here in the same chip, or through those HyperTransport links they can access the DRAM controllers in neighboring chips. In doing so, it's necessary to be able to route those packets appropriately. So this system request interface will handle that situation by building some packets and making sure that those packets contain some routing information. So those packets could be sent through this crossbar switch and possibly other switches at different processors so that they finally reach the corresponding DRAM controller and access the corresponding cache line and bring it to the cache. Okay? So it's no longer the case that those DRAM controllers just need a memory address. They also need some additional routing information so that the particular memory controller with the cache line attached to it, or storing the memory attached to it, is the one that's accessed. So you may think that we are introducing too much complexity because in order to reach memory controller that's located on chip, we need to build packets. But that's absolutely necessary if we want to fulfill the goal I mentioned before of unified interface for local and remote memory accesses, because this is the only way we can have this unified way of accessing memory. So in doing so, basically we define a single interface for all the cores, as I mentioned before. We have on-chip crossbar and routing so that we could access either the local memory controller or remote memory controllers. And we also have something that's not depicted here, which is a host bridge so that we could access the I/O devices as well. This is very quickly, this is the switch I mentioned before, and these are the different input ports for that switch coming from the external HyperTransport links, as well as the input port for the system request interface, each of them with multiple buffers. This is a slightly old slide with old buffer sizes. They have been updated over time. So now, once we have seen how to interface the processor cores with the rest of the system, now the question is, how do we attach a single device to that processor cores or to that processor interface? Well, the approach that has been followed in the HyperTransport technology is to implement high-speed point-to-point parallel links. Why parallel links? Well, first, because by running parallel links, we are able to increase bandwidth just by adding more wires. This is one of the reasons. The other reason is that we can implement a separate wire for clock, and therefore we can forward the clock, and this way we don't need to incur in the overhead of recovering clock. So that simplifies things a bit and allows for higher clock frequencies. So parallel links deliver high bandwidth and low latency. And why point-to-point links? Well, that has been mentioned before. We no longer have that high parasitic capacitance, and therefore we are able to reach much higher clock frequencies, so reaching the goal of very high speed. So with those parallel links, we now need to implement support for transmitting the packets I mentioned before, those packets that are formatted the system request interface. In doing so, one of the control lines associated with those data lines is not only the clock but the control line, and that control line allows us to distinguish between control packets and data packets. Basically, the idea is that by switching that line, we first send the packet header and then we send the payload. And that packet header will take care of providing all the information we need in order to reach the corresponding memory controllers or I/O devices. We have some additional control signals like power OK and reset that are needed for full system functionality. So now, in attaching that device to the host, we need to address the different layers. Let's start with the physical layer. The physical layer, HT implements low voltage differential signaling in order to provide the best possible signal integrity while running at the highest possible clock frequency. This way, it's quite immune to electromagnetic noise, and it's able to reach relatively long distances at very high frequencies. Also, in order to increase clock frequency to the maximum value, some pre-emphasis is implemented every time a bit switches from 1 to 0 or 0 to 1, so as to reduce the rise time and therefore be able to increase clock frequency to the maximum possible value. Well, in summary, HyperTransport supports multiple clock rates and also different link widths, and you can see here an 8-bit link and here a 32-bit link, so they both support the same packet format, simply with wider links those packets are transmitted faster, obviously. Also, HyperTransport provides, in supporting those multiple link widths, it provides support for not only a mixed set of link widths in the same system, but also for asymmetric links, where if we need to transfer a higher amount of information at a faster rate in one direction than with respect to the other one, we can support those asymmetric links. Now, moving to higher in the hierarchy, above the physical layer, we have the data link layer and transaction layers, which are both integrated into single one in HyperTransport technology. And basically, this data link and transaction layer requires some packet header, and that packet header is required to identify what's the role of that packet in the system. Is it going to be a memory read request or a memory write request or whatever? So that's identified there. What's the destination device? It's a memory controller, it's a peripheral device. What's the destination? And in case of accessing memory, what's the memory address? So all that information needs to be provided here in that header. And in those transactions that require some data, like for instance, a memory write operation or a read response operation, we also need to deliver those data. So those data follow the packet header, and we allow up to 64 bytes in a single transaction. An interesting feature is that as we use parallel links, there is no physical layer overhead. Here you can see a bit more detail for a data write sequence and a data read sequence. In the upper side, for the data write sequence, we send the control packet, which is 8 bytes long in the basic addressing scheme. Basic addressing scheme is able to address up to 1 terabyte of DRAM with 40-bit addresses. So with that packet header, we include all the information, including the memory address, and then it's followed by the data payload. For data read operations, we first send the read request control packet to memory controller. The memory controller decodes that packet, accesses the corresponding memory location, and then a response is returned with the corresponding data. Here we have some more details about the packet format. I'm not going to detail all the packet formats. This is just an example of the kind of packet formats that are used in this technology. Basically, for a request packet, we have here in the first byte the command, and the command basically identifies the kind of operation that is implemented by this particular packet. And then we have things like the unit ID. The unit ID identifies the peripheral device or the processor, the particular processor that is issuing this command. And then we have some address here in case this command is going to access some memory location. Indeed, if it's a request packet, it's going to access some memory location. So we need to specify the memory address here. There is also support for sending multiple packets that need to be delivered or processed in order, and then we include some sequence ID information here. This is another bit of information where you can see that the command field, here you have more detail, provides support for multiple packet formats, including the most typical ones: write request, read request, broadcast, atomic read-write modify operations, and things like that. There is also support for extending the address. I mentioned before that the basic packet format includes support for 40-bit addresses. But there is an extended format that provides support for up to 64-bit addresses. Okay, so both read and write requests can be extended so as to support 64-bit addresses. Here you have yet another example, this time for a response packet. Response packet format is like this. Again, we have a command field that indicates that this is a read response packet. And here we have some additional information like the unit ID. The unit ID, remember that it was the ID of the device issuing this request that now will be used to route the packet to the corresponding destination, because otherwise the memory controller would not know where to send those data that have been read from memory. In addition to this, we have some count field here, for instance, that indicates how many bytes are transferred, because, well, indeed not how many bytes, because these are chunks, how many chunks of bytes, so as to be able to indicate from 4 to 64 bytes in chunks of 4. And finally, some encoding of possible errors that could appear during the transaction. Here you have some more detail, including some additional message types like flash and thens for synchronization. Well, now that we have seen how to interconnect a single device to a host, let's see how to interconnect multiple devices to a host. When interconnecting multiple devices to a host, for instance, multiple peripheral devices to a host processor, we may need to do things like, well, access all of them with the lowest possible latency. And as we are not allowed to use a multi-drop bus, what do we do? Well, the simplest topology that could be implemented with point-to-point links is a linear array or a chain. And this is what we implement in HyperTransport technology. In that chain, there is a host at one side, there is a cave at the other side, and there are some tunnels in between. And those tunnels not only tunnel packets to appropriate destination, but if the destination is one of those tunnels, they are able to capture that packet and then send it to a corresponding attached peripheral device. Not only we can attach multiple peripheral devices in this chained way to a single host, but we can also bridge to other technologies, like for instance, bridge to PCI Express or to other technologies, or to peripherals attached to those other technologies. Here you have some more details of the different kind of devices that we can implement with this technology, so as to implement those chains that can expand themselves into trees. Because when we have, in addition to the host, we have the cave, which is the other end of the chain. We have tunnels that are those intermediate devices with some possibly attached peripheral device. We can also have those tunnels with a bridge to a secondary chain, and that secondary chain may be a HyperTransport chain or maybe a chain implemented with a different technology. So by using those bridges with a tunnel, we transform those linear arrays or chains into trees, so that we can plug a relatively large number of devices with a small number of hops, so that latency could be kept as short as possible. And finally, we of course have bridges without tunnels. Here there is an example of how do we route packets to reach those peripheral devices. Basically, we have here the command field, and the unit ID is used for reaching the corresponding device when sending those packets. And in doing so, remember that when accessing peripheral devices, some of them may be very slow. So we want to be able to pipeline multiple requests so that we can send a new request before the answer or the response to the previous one has been returned to the host. So HyperTransport includes support for pipelining multiple requests by having some response matching queue here at the host, and also some queue at the possibly implemented at the destination device, so that if that device is slow, it can queue multiple requests. So all those requests can be pipelined for higher performance. It's also possible to establish direct communication between different peripheral devices. We may need, for instance, to transfer data directly from an Ethernet controller to some disk controller, and this is possible with HyperTransport technology. In doing so, there are two addressing modes. One of them is host-reflected routing, so that the given peripheral device sends the request to the host, and the host reroutes that request to the corresponding peripheral device. This is one way of doing that. The other possibility is to have direct communication between those peripheral devices. Both modes are supported in HyperTransport technology. Of course, we also provide support for handling errors. If there is an error, that error is detected through a CRC, for instance, then the sender retransmits the packet. And finally, some notification is returned, or some acknowledgement is returned to the host or to the sender, indicating that the transaction has completed correctly. In case of multiple requests, we want to make sure that if there is a long request, the request, for instance, a read request that returns a response, and that response takes long to complete, we want to make sure that other commands can be interleaved among them, so that while the response from a given request is returning to the CPU, for instance, it's possible to interleave another request so that we can overlap both of them, and this way achieve the lowest possible latency. Well, now once we have seen how to interconnect multiple peripheral devices to a given host, now it's time to take a look at how to interconnect multiple hosts among them. In this case, as I mentioned before, we want to provide support for accessing not only local memory but also remote memory from every core in the system. In doing so, we usually want to implement support for cache coherence. Everything else is quite similar to what I already mentioned for peripheral devices. There will be simply direct communication from a given system request queue here to some memory controller here, in the same way we already did for peripheral devices. It's just the same unit ID, okay? The difference here is that we need to provide support for cache coherence. So how do we implement cache coherence support here? Well, basically, this is the whole picture. We will need to define some links, some HyperTransport links as coherent links, while some other links as defined as non-coherent links, so as to distinguish between links that are used for implementing the cache coherence protocol and therefore communicate one core here and some request from a core here to some memory controller in a remote device, and distinguish them from requests that go to some I/O devices. And this is done by appropriately configuring those links at boot time. At boot time, they are configured either as coherent or non-coherent links. And now let's take a look at some details of the cache coherence protocol. This is not handled, this technology is not handled by the HyperTransport Consortium, but instead it's AMD proprietary technology. I'm not going to detail all the aspects of those cache coherence protocols, but I would like just to mention some basic ideas and then show an example. Basically, this is derived from a Snoopy-based protocol, and you know that those protocols are based on broadcasting requests to every node in the system. However, here we no longer have a multi-drop bus. We have point-to-point links, and therefore we have to adapt that Snoopy-based protocol so that it could work on technology based on point-to-point links. So how do we do this? Well, it's a protocol that supports in the current version up to 8 CPUs, and it's based on broadcast. So the idea is that if we don't have a multi-drop bus, we simply broadcast a command, a probe or whatever, or for instance an invalidation request to all the nodes in the system. So we do so by using a 3-hop invalidation cache coherence protocol. Why 3 hops? Because we need some way to make sure that we avoid race conditions. And race conditions in the AMD implementation are avoided by serializing requests to the same memory line through the home node. This is the way those races are avoided in AMD's implementation. For instance, when there is a requester node that needs to access some memory line, then that request is sent to the home node. The home node, in parallel with the access to the memory, it sends probes to itself and to everybody else in the system, and those probes make sure that if there are copies, those copies are invalidated. If there is a more up-to-date copy, that copy is directly forwarded to the requesting node. And the issue is that all of those nodes need to return responses to the requester node so as to make sure that there are no race conditions. Let me show some more details on this. Basically, if P3 is requesting some cache line, some memory line that's in memory 0, then that request is routed to the corresponding controller here. In parallel with the access to memory, there is some probing that's broadcast to everybody. Those broadcasts reach every node in the system, and then the snoop responses also reach this system. Here we have the response from memory running in parallel with the acknowledgements, and finally this response reaches P3. P3 has already received all the acknowledgements from everybody else and also the data from memory, so it's safe. Now, in order to conclude this transaction, now P3 sends a source dawn message to the controller at the home node, and once this source dawn is received by P0, it knows that it can process some other pending requests for the same memory line. So this way, by serializing requests to the same memory line through the home node, we make sure that there are no race conditions. But this was the initial version of the protocol, and it's time to enhance it. So how is it possible to enhance it? Well, you know that the way to avoid broadcast operations is by implementing some directory. Directories are well known and have been implemented for many decades on large SMPs, but you know that they are quite expensive in terms of memory consumption for storing directory information, as well as in terms of latency because of the indirection. So AMD wanted to make it very efficient, so instead of implementing a directory associated with main memory, what they implemented is a cache, a directory cache, which kind of probe filter. It behaves as a probe filter. So this directory cache is very compact, and basically what it does is to replace this broadcast operation and avoid it whenever the memory line is clean. They do so in the following way. Basically, it's a sparse directory cache next to the memory controller, so it's associated with the memory controller at each home node. And the rule is very simple. If a line is cached, it has an entry in the probe filter. If a line is not cached, there is no corresponding entry in the probe filter. So with this simple rule, we dramatically reduce the size of the directory information required, because it's no longer necessary to have directory information for each memory line. Now, directory information is only needed for each cache line. And as caches are much smaller than the whole system memory, then directory information is also very compact. So compact that it fits within the chip. And by fitting it within the chip, latency is also quite short, because it's no longer necessary to access main memory to provide or to gather directory information. So this is the simple rule. If a line is cached, it has an entry in the probe filter. Obviously, that has some consequence. If a given request goes to the home node and it requires some cache line that's not cached there, it's not cached in any processor, and it has to bring it there, it has to allocate an entry in the corresponding directory cache. And if there is no room for it, some replacement policy is required. Okay. So it has some very nice features. First of all, there is no need for probing for uncatched lines, and this is very important, as I will mention later. And in case of cached lines, instead of sending a broadcast request to everybody else, there is a directed probe to request a copy directly to the processor that's the owner of the cached line. The benefits: significantly less bandwidth use, because some broadcast operations are simply avoided. If a line is not cached, no need for broadcast. And the other case is when the line is cached, but we replace the broadcast operation with a directed message to the owner of that cache line. In both cases, we can dramatically reduce bandwidth consumption. But not only this, we can also shorten latency. How? The most important case is when we run sequential applications. With the other protocol, it was necessary to broadcast requests or probes to invalidate copies that didn't exist. But as the directory, there was no directory information when accessing a new cache line, the processor didn't know, or the home memory controller didn't know that there were no copies. So it has to broadcast those probes to invalidate any potential copies. Now with this directory information, if there are no cache copies, the probe filter will provide that information, and therefore it's no longer necessary to send any request for uncatched lines. So in those cases, it's possible to dramatically shorter latency. Well, anyway, for more details, there will be a presentation, Blade computing with the AMD Magnicurs processor by Pat Conway in the main conference. Well, this is the response in case there is clean data. So the requester just sends the request to the home node. There is a lookup in the directory and a direct response. No need for probing. And in case where there is a dirty copy here, the home node sends a directed probe to that dirty copy. Sorry, the box here is missing. And this one directly sends the cache line, the requested cache line to a requester. Now, in this little amount of time that remains, let me briefly go over what's the future of HyperTransport. Some of the features that are implemented in HT3, as well as some future opportunities. So beyond the motherboard, well, HT3 provides support for interconnecting devices beyond the single motherboard by having a direct attachment to a CPU through some standardized connector, HTX, and therefore we can plug cards directly here. And this allows for more direct communication between a processor and some peripheral devices, for instance, some accelerators, a graphics card, not today, but maybe in the future, or some FPGA-based accelerators, things like that, so that we can provide, with respect to other technologies like PCI Express or PCI, we can provide lower latency and cache coherence support for the entire addressing space. It's also possible to implement link splitting, as I will mention later, when accessing those devices, so that multiple processors can access those devices in parallel. Here, without going into details, you can see from the first version of HTX to the current version, the increase in clock speed and bandwidth, as well as some additional features that I will mention later. One of them is quite interesting, is support for FPGAs where a fast device like a processor can be attached to a slow device like an FPGA and still implement some support for cache coherence without slowing the processor down. What's new in HyperTransport 3? There are a few key features that allow that technology to extend beyond the previous boundaries. The first one is link splitting, where you can take a link and split into two narrower links, and by doing that we can move from simpler topologies like this one to topologies like this one, where obviously those links are narrower, but it allows for direct interconnection from any CPU to any other CPU with lower bandwidth, but also lower latency. Dynamic power management is also extremely important these days, because you know that power consumption is becoming more and more important, and it will definitely be an issue that I don't expect it to disappear. It will remain to be important in the future. So being able to dynamically modify link width and make links narrower, or things like reducing clock rate and voltage dynamically, are key issues in order to be able to reduce power consumption in those technologies when the maximum bandwidth is not required. So in those cases, it's possible to reduce power consumption. And it's also possible, once we split a link into two narrower links, it's also possible partial shutdown so that we can save even more power. Obviously, in those cases, it takes longer to set it up again, and therefore we have to be careful. Another key feature of HT3 is the possibility to go to interconnect multiple motherboards by reaching further distances by using AC mode. AC mode basically means that we decouple links with some capacitor, but it's not just interleaving or incorporating some capacitor there. It's more than this, because we want to make sure that we are able to reach longer distances, possibly at the same clock frequency. How do we do that? Well, in this case, we can no longer keep using parallel links, and we have to switch back to technologies used by other interconnects like 8B, 10B encoding with embedded clocks, so that we need some clock recovery circuitry, and therefore we increase the overhead and things like that. But it's a good idea if we want to reach longer distances. Obviously, this is self-configured at boot time. And when combining AC mode and link splitting, it's possible to do things like this and provide configurations like this where multiple motherboards could be directly interconnected using HyperTransport technology. The only reason why this cannot be done today for more than 8 CPUs is addressing capabilities, is the size of the addressing fields in the packet format. Okay? I will talk about this later. And also, another interesting feature is hot plugging, where all the requirements for hot removal and hot plugging have been defined in the specifications, and therefore it's possible to hot plug devices. I'm not going into more details about this. This is the roadmap of this technology, how it evolved from HC1.0 to the current HC3.1, and something that's new that I'm going to talk about later, which is high node count, that will solve that problem I mentioned before, which is addressing more devices. Well, not going to detail, basically over these multiple generations, maximum clock frequency and bandwidth has increased, but also some additional features like the ones I mentioned before, AC operation, link splitting, hot plugging, dynamic link width and clock adjustment have been incorporated to HyperTransport technology. So, beyond HT3, what's the recent developments? What are the plans for the future? As I mentioned before, one of the main constraints was the number of devices that could be addressed with HyperTransport packets. So we needed to define packet formats that provide support for addressing a much larger number of nodes, and so we did. We developed the HyperTransport high node count specification that's 100% backwards compatible with the 3.1 specification, and at the same time it provides support for addressing much larger number of nodes. Basically, when doing so, we not only defined the new packet format, but we wanted to make sure that we define the whole system model. And we were considering physically distributed, logically shared memory systems, where, as opposed to current clusters, where shared memory basically reaches the size of the scope of the single motherboard, and communication among different motherboards is implemented with message passing. We were envisioning systems where the whole system memory and the whole set of peripheral devices could be accessed from every core in the system, so that we provide support for a global address space, possibly partitioned. So in that vision, we wanted to extend HyperTransport technology to provide low-cost, efficient support for that system model. And so we did. Basically, taking into account that we know that cache coherence may not scale to very large sizes, we don't impose cache coherence as a requirement. So we implement support for global address space, and the whole system may or may not implement support for cache coherence. That's optional, but it's allowed. And in case we implement some support for cache coherence, it's also possible to implement support for multiple coherent domains, so that not the whole system is coherent, but we can define multiple coherence domains. This is a very nice idea when combined with virtualization, where we can define multiple virtual machines, and we can define machines where the whole virtual machine is fully cache coherent, while some other machines may not be fully cache coherent if there is no need for that. But still, we will be able to access all the peripheral devices from every node in the system and from every virtual machine. Okay? So in order to do that, basically, what we did is we defined the concept of nest, which is an extension of the concept of node. And we defined some new packet formats. Sorry, I cannot provide details because this is still confidential for other than for top-level member companies in the consortium. But basically, we extend packet formats so as to provide destination and source informations with wider fields, so that we could address many more devices, obviously. And this has been done in a way that the destination identifier location is located as close as possible to the head of the packet, so that routing could be as efficient as possible. And also we took into account that some system manufacturers may want to implement small systems, some other system manufacturers may want to implement much larger systems. So we defined multiple packet formats so that different implementations could choose different packet formats depending on their particular needs. But for small systems or medium systems, it's very efficient. So we made it in such a way that we can implement it in a very efficient way with minimal extra latency and bandwidth use. So what we provide in that case is support for interconnecting a large number of hosts. And we know that in doing so, we need to define some addressing scheme as well as some new packet format, new topologies, and routing mechanisms. At this point in time, we just defined the new packet formats and the addressing schemes in those extended specifications, while leaving network topology and routing mechanisms to be implementation dependent, and therefore for manufacturers able to choose whatever they need. So basically, what we want to provide is to remove the bottleneck that currently exists in clusters due to the use of message passing, and using exactly the same infrastructure for interconnecting those nodes in the cluster, we replace message passing with shared memory. How? Simply by encapsulating HyperTransport packets over InfiniBand or over Ethernet. And in doing so, we benefit from existing interconnect infrastructure in large cluster systems. So in doing so, we can take advantage of heterogeneity. For instance, some nodes may have a smaller amount of RAM, some other more RAM, some other ones may implement a large amount of flash memory. We don't need to implement a large amount of flash memory in every node. If we implement it in just a few nodes, it's possible to access it from every node in the system, thanks to the fact that this is going to be a global address space. So this will provide resource sharing and modularity, hopefully resulting in less over-provisioning. For instance, we no longer need, with this technology, we no longer need to over-provision memory in every node. We can just reduce the size of memory in every node, because now a node can borrow memory from a neighboring node, thanks to the fact that we have a shared address space. This leads to better resource utilization and maximum energy efficiency. So, basically, this is the end of the presentation. Now, some commercial slides. Very quickly, HyperTransport has been implemented in many systems, even systems you may not expect. Obviously, desktop machines and clusters, but also in supercomputers, accelerators, and even places where you don't expect it. For instance, Chinese processors or Intel platforms. And now a few words about the HyperTransport Consortium. It's an open standard consortium that basically handles the non-coherent technology. It was founded in 2001 and basically takes care of controlling and promoting and licensing HyperTransport technology. So there are more than 60 companies in this consortium. And well, if you are interested in the slides, you have more information. And finally, well, this is how to access the website, HyperTransport website to get more information. And some additional sources of information, a book mostly by Brian Holden on HyperTransport 3.1, and some additional information sources like the specifications, white papers, and 3 books on interconnects, one by Hennessy and Patterson in the Appendix C, that was written by Professor Timothy Pinkston, who is here, and myself. And if you want a quick introduction to the topic, and 2 books on interconnection networks, one by Bill Daly, formerly a professor here at Stanford University, another one by myself and some colleagues. Thank you very much.
We do have some time for clarifying questions. If anybody would like to ask a question, please step up to the microphone and take advantage of that opportunity if you'd like. Doesn't look like there is. I'll let you go ahead and start switching that over. Okay, so it doesn't look like there are any questions. Oh, wait, maybe there is.
Okay. Sorry. Is the distance limit still defined as 3 feet, even with AC?
Sorry?
The distance limit that
oh no, the distance limit is significantly increased with DC mode. The standard limit is 12 inches when running a maximum clock frequency, while when switching to AC mode, if I remember correctly, is 1 meter running a maximum speed. So it increases significantly.
1 meter, okay.
Okay, thank you very much, Jose. I didn't believe he could do it, to be honest. That was 90 slides in 45 minutes. Jose is a professional. He teaches for a living. Please don't try this in your own presentations. I don't think Bob has quite as many slides, but next up I'd like to introduce Bob Safranek. He's a principal engineer at Intel. He's the current QPI chairperson across all of Intel. And he's one of the principal architects of QPI implemented in the Xeon 5500 Gangstown Nehalem EP processor. Bob.
Thanks, Chuck. And Jose, I have to admit, I was impressed. And to all of you, I apologize now. I don't speak nearly that fast. Okay. QPI is a proprietary interface, and this is our legal disclaimer that says this tutorial doesn't give you rights to produce it. Nor is there enough information for you to produce it from this tutorial either. So I don't know why I had to do that. As Chuck said, no, that's right, I'm supposed to stand over here. As Chuck said, the system interconnect is becoming increasingly important in how we connect to computer systems. The frontside bus or the multi-drop bus fundamentally is retired. For Intel, we will make a transition from all our high-end desktop, workstation, and all server platforms in about 15 months to basically go from a frontside bus architecture to a link-based architecture, or the QuickPath. So what is QPI? QPI for us is simply a high-performance, low-pin count system interface. I mean, that's what most of you like to hear, right? What does it do? Like HT, it basically provides us a definition of an interface that provides efficient scaling for the low end. As we grow up into larger base systems, like you'll hear a discussion later, I guess tomorrow, on our bigger part, Nehalem EX. And link-based systems basically allow you to have very diverse system topologies. And also, as Jose pointed out, if we look back at the frontside bus or bus-based systems, bit flips, parity errors, those were things that typically didn't happen, so therefore they were considered catastrophic events. As we go farther and farther and faster and faster, and the eye gets smaller and smaller, bit flips are going to happen. In fact, we don't even consider them errors anymore. It's just business as usual. And we must be able to identify those bit flips, recover from them, and continue on. QPI is more than just a definition at the physical link. Basically, it's a hierarchical definition. It's modular and flexible because features that appear in the mission critical space aren't necessarily valued or even desirable at what we call the efficient processing space, which is like a 1P, 2P systems. And as I stated earlier, QPI will be in every Xeon and Itanium processors based systems, well, our transition was late 2008, and we will completely transitioned over by early 2010. The first products that were initially offered, basically, in our EP space or whatever, are one-socket, two-socket configurations. Basically show just a simple, what I refer to as the triangle. 2 sockets, distributed memory, and a coherent I/O agent. But the architecture will also allow for much richer topologies, and those are typically the 4-socket, 8-socket machines, and those are fully or partially interconnected configuration. I just noticed that I always do fully interconnected, but that's just the way I draw things. And then on top of that, link-based architectures provide you an ability to define hierarchical-based systems. And we have several OEMs basically doing their own hierarchical-based systems for their own flexibility, for their own reasons. As I said, we've defined the QPI as a hierarchical-based definition. Starting at the very low level, what are the physical layers? What does the physical layer look like? And I have to apologize for this one. When we wrote the electrical spec, the persons who did that were defining the definition of a link. And so they were basically defining from a TX to an RX. And they interspersed the word link all over the place. When we got to the higher layers, we realized that we had 2 definitions of the word link. So in QPI, basically, we don't have a link, we have a link pair. And so we made up another term. What a link pair is basically 2 sets of unidirectional links. QPI uses low voltage differential signaling with a forwarded clock. And so we have basically a link going left to right and a link going right to left. And that's a link pair. As I stated earlier, we also include a forwarded clock. And a full width link pair is about 84 signals. QPI provides multiple link widths. And what I refer to as a full width link is 20 lanes wide. Also, we have a half width and a quarter width definitions. The initial products, Xeon 5500 and Bloomfield, basically hit the market with a 6.4 gigatransfers transfer rate. And for us, a full width link is approximately 12.8 gigabytes per second. And the link pair, of course, then would be double that, or 25.6. And being the chairperson, this was not my decision, but this adds a certain level of confusion. We calculate bandwidth differently. The bandwidth calculation is on a by 16. When you look at this number, it's on a by 16 number, not a by 20. Notice we have our width is by 20 wide, but our bandwidth is basically only calculated on a by 16. Because ultimately, when you see some of the formats, we have set CRC off to the side, and therefore we don't count that as part of the overall system bandwidth. Now, I could have said a lot of things about the physical layer, and, but some other features that we have done in QPI to aid in routing and other things is polarity inversion and lane reversal of a link. And so that makes it easier for routing. As we go to these faster and faster speeds, I/O pads used to be basically a big, a couple of big honking transistors. Not anymore. As we go faster and faster, you'll see that you have, transmitter equalization. Basically, you have receiver equalization and so forth. And as we go faster and faster, you can no longer physically touch the lanes. So how do you measure anything? How do you physically debug anything? And so the physical layer definition also includes, by definition, some probeless testing. Logically, this is what a link pair looks like. You basically have a component from, component A and component B for a given link. And before you physical people get out, start yelling at me, this is an architectural rendering, i.e. I did this. Really, the forwarded clock is in the center between all the data lanes. So, so just remember that. Transmitter equalization. For some of you computer architects out there like me, I thought this was a very enlightening area. This is not my area of expertise. That's my next disclaimer. Is what is equalization and why do we need it? Ultimately, all lanes, our channels, are slightly different. And all this equalization thing is, from an architectural standpoint, is multiple taps via some delay lines, or delays, I should say. A circuit which basically provides some type of coefficient or multiplier, and then a summer. And so you start off with a simple input of a pulse, and at each delay point, you just have that pulse replicated. Then, as that pulse is fed into that multiplier, a coefficient takes that signal and does something to it. And it could be a negative multiplication or not. And then at the very end, the summing logic basically puts the pulse back together again. At the transmitter, we don't care what the pulse looks like at the transmitter. We only care about what the pulse looks like at the receiver. And you'll find that across our different products, the smaller parts, Xeon 5500, the smaller parts have a certain number of taps. As we get to our bigger parts that go bigger distances, they have more taps for more control. Another view of this, of searching for those coefficients, is basically, if you don't know what the coefficients are, the receiver will look at that pulse and see fundamentally white noise. But as you go through training sequences, ultimately, as you adjust your pulses, you'll find an eye for a high and low going pulse. And during our power-up sequences, we do this. The logic will self-determine where that pulse is, along with where the clock edges are and things like that. And of course, this is ultimately critical to go 6.4 gigatransfers or faster. And probeless testing. Why do we care? From an architectural standpoint, we don't, we write things on pieces of paper or on slides or whatever, or we look at printouts or waveforms on the screen, but we don't know exactly what the hardware is actually doing. And basically, Chuck cares, I care. As we produce parts, if I can't see that, basically, if I can't touch those lines or those lanes, then how do I basically determine if it's working on a tester, or if I turn around, if it's working in circuit? So QPI has provided, at the physical layer, 3 levels of loopback. This first one is called basically, near-end loopback, digital near-end loopback. All this does is takes the TX and loops it back to the RX. Basically, so now you can just send messages to yourself, and you can test your internal logic. If there was a device or a board, like on a tester, basically, we now also allow for what we call local inter or intra-link, because it could be between links, loopback testing. And lastly, to round out the loopback trio, basically is when I have 2 parts in circuit, basically I can put one in loopback, so basically the other one can test itself. And we refer to that as remote loopback. Again, that's across the board in all QPI parts. Now, there's a lot of other things I could have talked about in the physical layer, but I thought those somewhat of the high points or some interesting topics. Hierarchically speaking, we now have we do have the link layer. And what does the link layer do for any link? Basically, it's the flow control provides the flow control mechanism between the 2 endpoints. We just use a simple credit-debit scheme. Also, it provides arbitration among what we refer to as message classes. QPI has 7 message classes, 6 are for protocol, and the 7th is for the link layer, or in the definition we call it special. Again, I didn't name it, as opposed to calling it just the link layer message class. It manages also the multiple virtual networks, basically the credit-debit scheme and how those message classes consume those credits and those credits. At the link layer, well, at the protocol layer, there's a dependency across all message classes. And we basically have a dependency diagram. But at the link layer, we have to guarantee that all protocol messages do not deadlock. So the link layer has to be fair across all message classes. And lastly, but I also think probably most importantly, is the link layer's job is to basically make sure that that 6.4 gigatransfers per second, that I can make that into 100% realizable bandwidth. So it's not important for me to go really fast, but basically to utilize the bandwidth I'm given. And lastly, basically, it does the error checking of the link. We expect that there's going to be some CRC errors, and we basically use a simple CRC and a link level retry mechanism when a CRC is detected. And on top of that, there's for what we refer to as the extreme and mission critical segments of the computer industry, self-healing characteristics as well. That's like recovering from a failed clock, forwarded clock, recovering from a failed lane. QPI, this is one area that we are a little different than most link layer protocols. The physical unit, basically, that 6.4 gigatransfers that fit, is defined by the width of the link, and that's basically 20, 10, or 5 bits wide. At the protocol layer, we deal with what we refer to as messages, or some people would say packets. At the link layer, we work at the FLIT granularity. A FLIT, by definition, is an 80-bit quantum of information, 72 bits payload, 8 bits CRC. For a full-width link, you'll see the 20 lanes wide. What you see is the CRC off to the side, and it's, a FLIT is four transfers. A half-width link is 8 transfers, and of course, a quarter-width link is 16. We'll get back to the FLIT definition and why we care about that in a second. Virtual channels. I mentioned earlier that I have 7 message classes, 6 of them from protocol. The special message class or the link layer message class, basically, I can inject a link layer FLIT anytime I feel like it. Right? That's the rules. But the other 6 message classes, it's the job of the link layer to ensure that they get sunk or they go across the link and not get lost. So we have 6 non-blocking message classes. Again, from a link layer standpoint, the message classes are all fair and equally basically distributed. We can provide no bias to any one of those. We then map those message classes to one of 3 virtual networks. Call them VN0, VN1, and VNA. That gives us a combination of 18 virtual channel combinations. VN0 is a credit that basically we provide at the packet level or at the message layer level. The same is true for VN1. VN0 and VN1 are there for deadlock avoidance and reroute capability on a failed link, and dynamic load distribution in a system topology. VNA basically is our adaptable virtual network. And what that does is it basically, if you send a 1 FLIT message, you consume 1 VNA credit in the VNA network. If you send a larger packet or let's say a 9 FLIT message, you consume 9, and so forth and so on. VN0 and VN1 are used for deadlock avoidance and guaranteed forward progress. VNA is basically adapts to the load of the traffic of the network. Oh. A couple of bits in each, and probably say this in the protocol section, but every message is basically consists of at least a header. And in that header, there is basically a couple of bits that say whether or not you consume a VN0, VNA, or VN1 credits going over. Okay, message classes. So given our link pair, the first 2 message classes that people always like to talk about, of course, are what we refer to as home and snoop. Basically, in the home message class, you'll find coherent requests and snoop responses. In the Snoop message class, you'll find basically spawned or basically sent snoops. For completions, we have two message classes as well. They're called NDR and DRS. Basically, non-data response and data response. NDR basically are like little completes or grants. And data responses are when you send cache lines and things like that. We also provide two non-coherent message classes. And these are called NCS, or non-coherent standard, and NCB. For those who know PCIe, we basically, you know about posted writes, posted and non-posted transactions. Non-posted transactions like configure read, configure write, in, out, non-coherent read, those appear in NCS. Things that appear in posted, like write combining writes, non-coherent writes, basically, those appear on NCB. So basically, PCIe just maps onto QPI. And lastly, the link layer has its own little message class. There's nulls, idles on that, as well as link level retries, commands, and things like that. I stated earlier that one of the primary or realizable most important jobs of the link layer is to allow to make the bandwidth provided at the physical layer is realizable. And the way one of the concepts we do this is called command insert interleave. And what this does is it allows for small messages, 1 flip, 2 flip messages, that are allowed to be interspersed into a larger data stream, a larger packet. And the benefits of command insert interleave. It allows us not to bring, now that we have CRC on flits, basically we're allowed to insert at flit granularity messages in between a bigger packet. But more importantly, because we have CRC on individual flits, we don't bring in the entire packet before we route it to someplace else, or allow the data to be consumed by core. Basically, we do this at basically 8-byte chunks. This also allows us to, as memory comes streaming off out of memory controllers, basically, if the memory runs at a slightly different frequency, or there's a correctable error, a correctable bit flip on memory subsystems, if there's a bubble, we don't have to bring the entire 64 bytes in before we start sending it out. We just, as it arrives, we start sending it out. Okay, again, no storing forward. And I guess that we just said minimizes lead-off latency. This is very important in, of course, efficient, what we refer to as our EP systems, which are the Xeon 5500s and things like that. An example of what this is, and I liked Jose's slide much better on this one, is a data transfer is 9 flits, header plus 8 datum. As we start sending off that first header flit, let's say a bubble was injected. I don't care why the bubble was there, whether it was injected because of a frequency crossing thing. I'm allowed to insert single flip messages or double flip messages into the data stream. And those messages are like requests, snoops, snoop responses, completions, what have you. Again, if there's another bubble in the data stream, I can purposely choose to insert a command if I so choose. One of the benefits, of course, of doing this is you allow the first data to arrive, giving you your lead-off latency, but then basically you now can shorten the latency of other transactions by injecting someplace else in the data stream. And lastly, anytime so needed, we can inject a link layer flit, like retry probably is the best example here, is basically saying the link going the other way had a CRC error and basically a replay from point X. CRC protection, okay. Again, CRC is based on a flit. So because I only have four transfers and a full width flit, I don't need a CRC32 or big heavy CRC tree. I just need a CRC8. Once I bring in those 8 bytes, I'm allowed to consume those 8 bytes at the time that that flit is brought in. The general properties of CRC8 over just 80 bits, it protects you on 1, 2, 3-bit errors, all odd number errors, 99% of all burst length of 8, 9 errors, and 99.6 with burst length greater than 9. In the segments that this is not good enough, like extreme, in some cases extreme, the extreme Xeon servers, or mission critical, we also provide another ability called rolling CRC, which is a concatenation of CRC between the flit up in front of you and the one and you, and it changed the system. I think I have very little respect for routing layers, I've been told. All routing layers, in my opinion, are kind of the same. And so someone said I had to have a routing layer slide, so I put one in. At the source, at the requester, it's fundamentally address-based. At the intermediate points, there's a destination node ID in the headers, and basically it's based off of that. Routing layers, basically, these should be configurable, and they're done via programming, via firmware. They're not hard-coded. And this allows us to basically use a changeable routing layer in those mission-critical spaces and things like that, to route around failed links when they do happen. VM1 allows us to route around dynamically when a link fails and maintain coherency, and then we can quiesce the system to turn that link off to avoid any additional failures. In addition, this dynamic programmability allows us to support what we refer to as online star, online remove, online add of a socket. And of course, that also allows for dynamic partitioning, hardware partition, not virtual, of a system topology, in a system topology. 12 minutes. Okay, I can do this. Protocol layer. Basically, the protocol layer, basically, what does it define? It defines coherent and non-coherent transactions. In addition, even though we don't have the frontside bus anymore, every line of code written for IA32, basically, we have to support. We can't break that paradigm. So all those things we grew to hate about the frontside bus, we basically have to provide some analogy to emulate that behavior. And we refer to this as virtual legacy wires, or VLWs. In addition, besides the link layer having its own power management, which discussion I threw out because I didn't have enough time, we also, at the protocol layer, allows for at the protocol layer, the passing of S state, C state, P-state messages. I think most of you have already heard at the protocol layer, Xeon 5500 is a source snooped based coherency protocol, not a home snooped. We also do have home snoop ability as well in the QPI spec. And basically we have I'll get to the caching agents. I'll skip that to the next one. And then the protocol for coherency will be, is a 5-state protocol: modify, exclusive, shared, invalidate, and forwarded. And we have only one ordering rule about message classes. And that rule is, in the home message class, remember that's the one that carries snoop responses and home requests, that for a given address, the snoop's responses and requests must maintain order, must be in the order of issue, must arrive in the order of issue. Also, this protocol uses pre-allocation, so there are no retries, and basically there's a built-in conflict resolution. So once there is an address conflict, the home agent basically picks a winner and then cycles through the next one, the next one, the next one. Okay, so again, guaranteed forward progress. Agent types. On the front side bus, we didn't have a thing, we didn't actually have a concept of configuration read or write. Here we do, okay? Configuration agent, kind of self-explanatory. Caching agent. Its functions are, it issues requests to the home. It could be after, it could be before a cache miss, but let's just call it after a cache miss. Supplies data on snoop hits or forwarded requests from home. It detects and acknowledges conflicts and responds with let's repeat. Okay. Home agent. The home agent basically is the ordering mechanism in the system for a given address. Remember, a home agent is basically the front end to a memory controller. It tracks every potential outstanding request and recipient of all snoop responses. If those snoop responses are implied or spawned, that's, it does keep track of those things. It also, the home agent decides on conflict who wins or who gets the data next, or change the requests. Message class dependencies. For PCIe, non-coherent standard, non-coherent, just posted and non-posted, fundamentally, this is your dependency diagram. Those green, the two green and the bottom two blue bubbles, basically. And fundamentally what that says is reads push writes, writes pass reads, and you need completions and datum. Home requests basically spawn snoops, or can spawn snoops, and they're dependent on data responses and data completions. And basically with that, this simple diagram, basically we prove that we are deadlock free. Our cache flow diagrams that we use in the QPI spec are based on this Rosetta Stone. Basically transactions, we have caching agents labeled across the side. We don't care about the topologies, and basically, and for a given address, we have a home agent, always a home agent. Ordered messages on the home channels are basically those dashed lines, and when we have a green dot to say I consume a resource, a yellow dot means I release all my resources. So what does a coherent transaction look like for QPI? After a cache miss, basically, B will issue a request in home to to the home, wherever that home is. In addition, snoops can either be implied or spawned or sent to the other caching or coherent agents. Again, when they also, in this particular case, provided response I as their snoop response, they send their snoops or responses to the home agent. Hopefully, that always happens underneath the access of the data access of memory. And then a completion is sent, in this particular case, DRS, to the requester. Another transaction to kind of compare that to, would, of course, would be an RFO. And in this example, instead of having complete misses, this transaction basically says that it's held in a cache someplace in M. That's the beginning state over B. That M is what that signifies. In this particular case, the transaction happened from A, which is red, and hopefully you're not colorblind. In addition, there are corresponding snoops sent to the other caching agents. B basically says, it hit my cache, here's the data. At this moment, once the data is received, that data can be consumed by the requester. Whether or not everyone has seen the snoop responses or not is irrelevant. The data can immediately be consumed. So basically, that first 8 bytes of data is forwarded right to the core. And it basically transitions to M at that, if it was to modify, if its intent was to write. In addition, B will signal to the home agent, data was forwarded. In QPI, the requester only receives the data one time. So the data, once he receives it, he knows he can consume it. We send cancels, but that's irrelevant for our memory controllers. Once all the snoop responses have been collected for a transaction, then basically the complete is sent from the home agent. At that time, all the resources can be released. Also, at the time of the yellow dot, the requester now can expose to the rest of the topology whatever it did to that data. Until that completion is that time, it can only people behind that caching agent can see that data. And we added one more flow, and basically it's called the invalidating write flow. And this is specifically for the EP segment, the low end. And what this does is for like a coherent IOH, used for IOHs, we send the, what we do is we fundamentally have this invalidating write flow. It looks like an RFO. But the main thing it does here is it flushes all data to memory, because its intent is to fundamentally write, partial write or full or partial line. It is irrelevant. In my particular case, it was a complete miss. We now give the grant or the ordering point to the IOH. At this moment, that transaction, whether or not it was speculative or not, is now can be ordered. So basically, the producer-consumer model of PCIe, that's the ordering point that it must adhere to. At some time later, data is then written back to memory. With this flow and one other rule, I have a coherent IOH that I never have to snoop. And so you heard me previously say something like that, oh, by the way, snoops are either sent, spawned, or implied. So with this particular flow, basically, I have no snoop filter, I have no directory, I have no directory cache, but I still maintain And I send those snoops to the IOH, but I still maintain coherency. That's quite the whirlwind for me. Where is Intel heading with this QPI thing? It will be our server interconnect strategy for years to come. Things will change. I won't say that they won't. There'll be some coherency modifications. We'll go faster. We currently are copper-based. Where all that stuff heads, sky's the limit. Hopefully, and this is something that Jose and I drill into, QPI, HT are not definitions about a link. They're definitions about a topology and the rules to build dynamic-based systems. One thing we have to do is all that code, all those billions of lines of code out there, we have to basically form, fit, and function, execute those as if they were executed on a front-side bus. Basically, we want to provide a low-end system capabilities, which has some bandwidth and latency components to those market segments. We didn't talk about the power management flows, but you definitely need those in our system, our computer rooms today. And in our larger or high-end, the extreme and mission-critical segments, basically, we provide an infrastructure for RAS. And those include clock fail-safe, link self-healing, rolling CRC, ability to reroute around a failed link, and of course, the ability to statically or dynamically partition systems and OL star. And intersocket, I never even mentioned that, intersocket DIMM sparing, and DIMM sparing, memory mirroring, RAID, etc. For information, there is a white paper at that website. There is a book. I'm told it's available this week. I don't know what that means. I don't know if that means today is Sunday, it's available today, or it's Friday at 11:59 p.m. But it'll be available via Intel Press and through Amazon. And there's also a Mindshare class taught by Mindshare. Are there any questions? Yeah, thank you.
So this is Ken Chen from Rambus. It's interesting that in contrast to HyperTransport, you support asymmetric arrangement of the link, but it seems you mentioned that you always form the link pair, like the one direction is equal to the other direction. Is that true? Do you really need that?
No. By convention, the links are symmetric in size.
But you don't need that.
But no, there's nothing that says it could be asymmetrical. And in fact, when in the failover mode, where you have a failed lane or clock failover, immediately that direction will go to half width.
Okay. So the other question is clarification. So in one slide, you're saying your payload is based on 8-bit or 16 bits. Mm-hmm. But the other slide, you're saying in the link layer quantum slide, you're saying payload is 72 bits. Is there any? Okay, so for a FLIT basically, that's a good question. A FLIT is basically 80 bits. And whether or not it's full width, half width, the definition is 80 bits, doesn't change. So if it's 20 bits wide, physically, basically 20 times 4 is 80, or 4 transfers. If it's 10 bits wide, it is
8 transfers.
Yeah, but where does 72 come from?
72.
is I.
Oh, I see.
9. It's 9.
72. Right? So 80 bits, 8 bits CRC, subtract out 72, 80 minus 8, 72. Now, on the data side, basically, we say that when you do data transfers, then basically you only put data only on 16 bits of those.
Okay.
In fact, I'll give you the exact translation. 6.4 gigatransfers says 1.6 gigaflops go this way, and 1.6 gigaflops go that way. In Xeon 5500, if you send a remote request, that's 1 flit, and basically for a cache line, you get 9 flits back. There's no snoop sent to the other caching agent because it's spawned locally. So basically, if you look at your transfers, you have 1 flit going this way, 9 going that way, and if you had the guy on the other side doing the exact same thing, you have, for 2 cache lines, you have 10 flits going this way and 10 flits going that way, or basically, a given link supports 0.16 or 160 million cache lines in both directions. That's the calculation.
Okay, thank you.
Okay.
Hello, I'm Todd Besnick, currently not affiliated. Bob, I'd like to thank you for taking the time to come and give this great talk. And I noticed that neither you or Jose characterized the power usage of these interconnects. And I'm wondering if you can give just, say, some kind of idea, like, say, a 20-lane QPI, running at the full 6.4 gigatransactions per second, what sort of power envelope that would have?
Well, a couple things. One, you're right, I didn't. 2, I can't remember a number to save my soul. I can remember concepts, too, but basically, it's low voltage differential, so the current is pretty much fixed. Now, the reason why I don't quote those numbers, and the reason why I think Jose can't quote those numbers is these links have power management modes in them. So basically, when the link for Xeon 5500 isn't being used, the
so saturated.
Saturated? I don't know that number.
So essentially, it's being a processor architect. I always had some kind of idea how many watts, the front end of the pipeline, the disambiguation logic was going to use and all this. So apparently, this just isn't a power concern. Otherwise, you just know it.
Oh, it's very much a power concern. But all the different products are different. And so the IOH's power link consumption is completely different than the processors, number one. Number 2, the power of those links also vary based on what watt skew that those parts are in. Now, usually that number, though, is provided by on the spec sheets. I just don't know what the number is off the top. What we quote as the real number, which is a conservative number, but I don't know what that number is. Sorry.
Hello, David Cantor from Real World Tech. I actually had a question for you about the firmware and routing. So it sounds like you can adjust the routing tables on the fly in response to failures, which is nice. But what is sort of the frequency that you anticipate probing the routing tables at?
You mean when a message?
Right. I mean, you need to have pretty fast firmware, right?
Well, no. So the firmware basically is there only to program it. Once it's programmed, it's all done. The routing is actually done in hardware. And to be fair, your definition was slightly inaccurate. You said that we can change the routing table to paraphrase willy-nilly, which is not correct. Right. What we do, we have a mechanism to quiesce the system, whatever that topology is, and allow for one individual, one entity, to change those tables and then unquiesce the system in short order. Now, once it's routed, then basically the frequency of accessing the routing table is fundamentally cache miss at the source. It's equivalent to that number. And basically cache or message arrival at a receiver.
Okay.
It's those two numbers.
All right, thank you.
Okay, I'd like to thank our speaker one more time.
Thanks, Chuck.
Our third speaker today is Jasmin Ajanovic. He's a senior principal engineer at Intel. He's the lead I/O interconnect architect at Intel. He's architect of the PCI, he's the chair of the PCI protocol committee as well as the bridge work group in PCI SIG. So let's start it again. Let's welcome Jasmin. Thanks.
Thanks, Chuck, and welcome. So let me just briefly tell you what you're going to hear today in this session. I'll give a brief PCI Express architecture overview and talk about mainly about the next incoming generation of the PCI Express, third generation of PCI Express. Let me first kind of take a quick poll. How many of you are familiar with PCI Express technology in general? Okay. Just to understand how much I spend on the architecture overview. Because the presentation here is really focused on what's coming in a third generation rather than the baseline PCI Express. So PCI Express is a technology that evolved from the PCI that some of you know. It's basically started in 1992. Very strong organization, PCI SIG, with 500 plus members. And so far, we delivered probably billions of systems with PCI or PCI Express. When you look the run rate of 150 to 200 million systems annually of the PC class and the servers, PCI Express is pretty much in every one of them. As far as just brief overview, from a physical point of view, PCI Express is point-to-point full duplex. We used differential low voltage signaling, embedded clock, so also allows for AC coupling, and it was defined as a scalable from a day one in terms of both width and a frequency, so you could dial in the amount of performance and bandwidth depending on application needs. PCI SIG developed a bunch of successful form factor standards. That was essential. When we talk about a mainstream, we talk about the connectors that are 50 cents, for example. That also has some requirements for some limitations, pragmatic limitations in terms of what kind of technology do we develop, because it needs to be something that supports high volume manufacturing. PCI Express has a number of advanced capabilities on the top of the baseline, depending on the application needs. Obviously, the one who implements PCI Express in a small form factor netbook or even a PDA class of machine versus the one who implements PCI Express in a high-end server, they want to have a different needs, and we don't want to impact throughout the entire spectrum. We don't want to impact everybody with the same limitations or same requirements. Increase in I/O bandwidth, that's basically inevitable. Every 3 to 4 years, we increase the rate, the bandwidth for 2x typically. A reduction of latency, improvement of the power. It's actually energy efficient performance. Those are all driving actually new generations of PCI Express. This is going to give you just a brief view on a roadmap. As we know today, we started deploying the products in 2003 with the first generation that ran at 2.5 gig, followed by successfully deployed Gen 2, where the products emerged in 2007, and now by now Gen 2 is fairly mainstream. Somewhere between deployment of Gen 2 and today, we develop additional standards on the top of the PCI Express to support I/O virtualization and device sharing. I'm not going to talk about those today, but I'm going to focus more on the last generation of the PCI Express, the Gen 3, and actually features and requirements that actually drove this PCI Express Gen 3. Just one thing quickly for calibration. PCI Express comes in, as I said, scalable width. So looking from by 1 to by 16, if we normalize on by 16, first generation gives 8 gigabytes per second, and the last generation will give 32 gigabytes per second on by 16 link. Architecturally, PCI Express can support by 32 as well. So this is tremendous amount of bandwidth that actually even exceeds some of the processor interface bandwidth today. As I said, continuous improvement, and we will be doubling the bandwidth every 3 to 4 years. I'll talk a little bit about 3.0 electrical interface and requirements. I think the key success of the PCI technology, broadly speaking, and PCI Express in particular, is the compatibility and backwards compatibility. Every succeeding generation needs to provide backwards compatibility between the PCI, which was fundamentally the parallel bus, and PCI Express. We provided that through the bridging. Once when we got into the PCI Express, our mantra was actually that you would be able to plug PCI Express Gen 1, Gen 2, and Gen 3 cards into the same connectors, and we're expecting this to be done to the same degree with following generations, Gen 4. So that's the key requirement for that was actually limiting some of the and actually driving some of the definition of the third generation of the PCI Express. The other thing is the expectation that in every generation you want to have a 2x bandwidth improvement, in this case over the 2.0, which, as I said previously, runs at 5 gigatransfers per second, which would tend us to say, oh, okay, Gen 3 is 10 gigatransfers per second, but you will see that that's not the case and why, but we still managed to get the 2x bandwidth. The other thing is the cost structure. We cannot really increase the cost structure significantly. I mentioned previously the volume connectors for PCI Express cards are 50 cents, and that's really, you know, for the high volume manufacturing, I think that's also essential. We want to preserve on the platform existing mechanism for synchronizing the transfers, meaning data clocked and common clock architecture, and make sure that current materials are and high volume manufacturing ingredients are viable as well. This last bullet shows actually what are the expected topologies in terms of the channel length. On a mobile, we see relatively a short channel of 8 inches. On a desktop, we see a bit longer, 14 inches typically with one connector. And I think the one that has the biggest challenge is the server, that we see the interconnect spanning over the 20 inches and 2 connectors, which is basically to support backplane type of topologies. So these are the requirements that we took into the development of the next generation or third generation of the PCI Express. And when we look at the solution space, as I said previously, you know, logically we would go to 10 gigatransfers per second. However, analysis done by Intel and also supported by the evidence of the other members of the PCI SIG, and I forgot to mention PCI SIG is the organization that has you know, companies like IBM, Hewlett Packard, AMD, Microsoft, Intel, and others driving most of the mainstream development. analysis done by Intel and corroborated with also the similar findings by the other PCI SIG members show that doing the 10 gigatransfers per second would be a significant challenge. We would be forced to break the backwards compatibility, or we would require some sort of new materials which will break the HVM. So this set of diagrams is really, you shouldn't read these as a diagram, but the discrete points that are connected. The table here shows the type of improvements in terms of equalization techniques that are used on a transmitter and receiver side. It's kind of set of recipe that was analyzed to see if there's a solution space for 10 gigatransfers per second. Even using a best of the breed equalization techniques both on the transmit and receive side didn't really bring the 10 gigatransfers per second into the mainstream solution space. Marginally for the client, but definitely not for the server. So the solution that we found is really going with 8 gigatransfers per second. Now the question and challenge is how to get the 2x of the bandwidth, because from 5 gigatransfers per second to 8, we're not getting inherently twice as much of performance. Well, and solution is found in changing the, in a third generation, the encoding technique that is being used. PCI Express on the day one relied on 8B, 10B. That was a technology developed or technique developed and very, I would say, mainstream technique used in industry. We delivered 2 generations of the PCI Express using that mechanism for encoding, and realized that in a third generation, if we want to make a good trade-off between the complexity of encoding the information and how much do we push people in terms of the signaling rates, that we will maybe take the compromise and require new encoding scheme, which will make a little bit more difficult to make the backwards compatible, because you'll basically be dealing with a bimodal type of interface, but we felt that that was the right choice. So 8 gigatransfers per second, removing 8B, 10B, that was imposing 25% overhead, and using a scrambling technique and some sort of new framing mechanism that I'm going to show in more details, was found as a solution. On the top of that, more capability on a transmit in terms of the emphasis and equalization, and also on the receive side. Fundamentally, the third enabling factor for 8 gig is also the bandwidth optimizations for the PLLs. I'm going to spend a little time and try to demonstrate what is this new encoding technique that is developed for the third generation PCI Express. And by the way, as a disclaimer, specifications are not complete yet. They're in 0.7 draft stage that will be released sometimes in September. We're expecting the finalization of the specs early next year. So technology hasn't been, I would say, completely proven yet, but there's test chips, test components done by the members of the SIG that are driving the definition that suggests that we would probably reach the milestone in 2010 and deliver the complete specs. So again, going back to the encoding, the problem statement was, how do we get twice as much of bandwidth while not going to doubling the operational frequency? These reasons that I've already mentioned. And one thing that, if you're familiar with 8B, 10B, is that it was very simple way by creating so-called 10-bit character to create the control characters in a serial data stream that will allow framing of the packets and also supporting some special low-level protocol, signaling messages, that sort of stuff. So if we remove the 8-bit, 10-bit, all of that is pretty much gone. So we needed actually to kind of step back and figure out how we recreate a notion of through the new encoding scheme, a notion of these special characters. Okay, thank you. So I switched to the better laser printer Gen 3. I hope it's going to work better. So the new encoding scheme actually relies on two levels of encapsulation. This is a representation of the by 4 link of the PCI Express. What we're trying to illustrate here is that there's sort of encoding that goes vertically per lane. 128-bit is a quantum of data that we call the block with 2 synchronization beats, becomes 130 beats, and that's actually per lane encoding. So per lane you could decipher these blocks of data. How they fit into the packet and where the boundaries of the packet, that's a different thing. The packet is defined across the lane with some special sort of beat stream pattern that will define packets like link layer packets and protocol layer packets. And I'll show you an illustration of that in the following slides. In order to preserve DC-DC balancing and actually provide the embedded clock information, technique that is used is additive scrambling, and information is basically minus the synchronization characters when it comes on the lane is scrambled on the transmit side and scrambled on the receive side. Transmit and receive mutually understand what is the algorithm for scrambling and descrambling, and that's done to the during the installation, and also could be reinitialized during runtime. This gives you an illustration of how the beats are mapped on by one link. Essentially, the Gen 3 symbol or character is 8-bit now instead of 10-bit as in the previous generation. And the information is, if we look, 128-bit payload block, how it's being transmitted over the by one link. Obviously, the symbol 0 goes first, and then up to the symbol 16, there's synchronization, preamble, 2-bit information, and this whole block is the 128, it's 132-bit block. So how that looks on the by 4 link, on by 4 link, again, the block is per lane. However, if you have a packet that consists, let's say, of 64 symbols or 64 bytes of information, how they're going to slice across these lanes. Symbol 0 goes on lane 0, 1 on lane 1, and it kind of gets interleaved. And so you have a packet information that is actually spliced over the multiple links. Still, the basic fundamental block of information is per lane basis. So this was trying to explain how the just raw beat information is being placed on the wire. We needed to define a method for encapsulation of or framing of the information so that we can define the delimiters of the packet. If you're familiar with the prior generations or current generation of the PCI Express, you would know that this part is the format of the so-called TLP packet. It includes the sequence number, has some reserved beats, and has the 10-bit in 8 characters that are start of the packet, and actually start of the packet and end of the packet. Well, in this picture, we don't have a start of the packet, end of the packet. We have this front-end kind of a header or new framing information header that tells the length of the entire packet. So rather than having the simple 8-bit, 10-bit start and end characters and pay the overhead for, you know, two extra beats per byte of information, we developed this scheme where actually reading the same footprint of the packet, so packet did not increase, we actually have much more efficient way of communicating the information where we identify the length of the entire structure to the length beat. STP is actually beat stream that is the pattern that indicates this is the start of the transaction layer packet. Then there's a length, and that both STP and length are protected by the CRC information. CRC just for this new header, and also there's a odd parity bit that covers the entire 15 bits. This gives actually reliability at the level and beyond of what we had with the prior generations of the PCI Express. So we came with a new method of encoding. We improved the efficiency. We didn't compromise, but we actually did improve the data integrity. Obviously, it is a trade-off that you know, it's a bit more complex scheme to implement than in the prior generations, but we felt that industry was moving on that tangent, that it might be easier to deal with a kind of a logic level complexity than to deal with the signaling that will be breaking the, as I said, high volume manufacturing, and will be very difficult to implement. PCI Express has two types of packet protocol, transaction level protocol packets, and also data link level. This picture resembles how the data link layer packets look like. They didn't change in terms of the footprint. So again, we improved the efficiency. Previously, we had the start and end. Now that was replaced with the beat pattern that actually indicates that this is the data link layer packet. Now, to put this whole into perspective, example of the sequence of transaction layer packet followed by the data link and followed by the idles in a by 8 type of configuration. We have first at the beginning of time, or at the beginning of this block, we have a synchronization character that is the beginning of the 128 or 130 block that is per lane. And after that, symbol 0 you know, will be the one that includes the definition of, to the beat pattern definition of what is the type of the packet. In this case is the TLP packet. So the STP sequence number, and that structure actually defines how long where's the boundary of this green field, which is the TLP packet. It's followed by the data link layer packet, and then there's nothing else to transmit, and that shows as a logical idle on the link, which is driving all zeros, and then follows by another packet. This example also shows that transaction layer packet is crossing the boundary of 228, 130 beat blocks that are, you know, and suggest that this is really two orthogonal schemes that work together. So that's actually probably all what I would like to say at this point. So now let's put this whole in a perspective. Let's show the example of the transaction layer packet. A transaction layer packet that consists of the header information, consists of the data and link level CRC, and also there's a sequence number that is being generated by the link layer. That goes into some sort of a framing logic. So that framing logic will actually need to parse the informational structure and create this new informational content that is these new micro headers for the framing. And once when it creates that, it will put that in the proper lane. This information is still in unchanged data informational content from whatever is the original data here. And then it goes to the scrambler that scrambles all of the bits to satisfy the requirement of the DC balanced interface and provide embedded clock information. And then the scrambled information goes across the lanes and gets transmitted to the receive side. So this is the example of the transmission of the TLP pack. This definition of encoding is in fairly solid state, and I would say that I think we come up with something fairly pragmatic that is not overly complicated. It is a bit more complicated than just simply go with the 8B, 10B scheme, but I said previously 10 giga transfers per second would break the ecosystem. You know, yeah, we could come up with the better materials and with more expensive connectors, but you know, 50-cent connector is what OEMs are expecting, and none of us, neither system vendors nor component vendors, will be making money going forward if we would increase the cost of the systems. So that was the electrical and encoding layer. I just wanted to give you a brief glance on what's coming. Obviously, there's no substitute than to go either read the spec or attend some of the events. PCI SIG has developer conferences. One was happened only I think just two months ago here in a valley. So if you're interested, attend those, and there's a website pointer link that I will show at the last slide. Now I'm going to talk about the protocol extensions, which are driven mainly by the desire to improve the performance of the system, to get good energy efficient performance, and it was also driven by some new usage models. We put these protocol extensions in these buckets. I'm not going to read each of these items, but I'm actually going to cover some of the most important ones in more details. The one thing that I would like to explain how the PCI Express and how the PCI SIG manages deployment of the new capabilities. We have a mechanism through a software configuration to declare the new capability, so that that provides the backwards compatibility. Only when you have system and components that have a matching capability is enabled. All capabilities are defined as optionals, which would beg the question, okay, why do you define them there if they're optional? People are not going to build it, but we believe that it's a self-regulating mechanism. The capabilities that are important for the products, people will implement them in their products and will build them. And that was the, I think, in a way, success story of even with the original PCI since '92. So let me go into more details on some of these. Transaction level processing hints. The background and the problem statement is that although in some systems currently and in the past there's some small I/O caches were implemented, they're pretty ineffective. I/O was mainly treated as a second-class citizen on a platform in terms of the how to tap on a memory and a cache hierarchy infrastructure. We tried to fix that problem by providing sort of hints that will be available to the I/O device to tell to the processor a cache hierarchy complex on what would be the best way to manage the data flow. These transaction processing hints, the goal is actually to, for the I/O, to suggest if certain data could be installed directly into the cache, if certain data could be taken out of the cache, if certain data will have a retention policy so that even in some cases, if it's I/O data, it may make sense to make the allocation into the cache. Now one would say, hey, but this could compromise the CPU performance. Well, if you look at the modern processors, we are going to many megabytes of the caches on a chip, even going into the dozens of megabytes. Taking some small portion of that for improving the I/O could actually improve the overall system performance. And I'll try to illustrate on a few examples that are coming that it would actually help reducing first the overall usage of the links like HyperTransport cache coherent or QPI, which we call system interconnect cache coherent links, and also would reduce the footprint that I/O traffic imposed to the memory subsystem, meaning there'll be less memory transactions, and that will give you back bandwidth and will reduce the power. Well, actually, let me just point to this. This is the information that is, came from Intel. We did some performance analysis on how the transaction processing hints could help to reduce the miss rate in a system, miss rate as measured by the CPU on the data that was driven by the I/O, and we look some common benchmarks from TPCC that is more I/O to DGEM that is more kind of a acceleration processing type of implementation. This one had the best improvement in terms of the performance. So this is just to go over the flow of what happens normally in a system. Basic device writes and reads, and then I'll contrast that to the one with improved hints. So typically, device will write the data. There will be snoop of the system caches. If the data is in a cache, there will be write back in some systems that are not very optimized. There will be separate write back, and then there will be separate writes by the device. The device will notify the CPU that data is in a memory, and then the CPU will at some point later read that data into the cache. You notice that in this particular scenario, that data might be in a cache to start with. So we had all these, 4 transitions without really, which were really unnecessary. So if we could provide the hint by the device that data is probably in a memory, or that data, the data is in a cache and can be updated directly into the cache, then after the snoop, the update happens directly within the cache, and CPU would read information out of the cache. In this case, you wouldn't actually see memory traffic whatsoever for the same type of a sequence. In worst case scenario, in a multi-socket system, this could be cache-to-cache transfer depending of where the I/O transaction goes. But nevertheless, it will not require a memory transaction. So we're reducing in this case, we're reducing both memory and system interconnect bandwidth, and that actually comes with reduced power as well. Now let's go to the example of the device reads. CPU writes some data into the memory, and in this case it will basically reside in the cache and then pings the device to come and pick up the data. Device will perform the read that will cause the snoop of the system caches. In conventional systems, this will impose the write back to memory. In some cases, data will be snarfed by being written back to the memory. In some cases, you'll generate another read to the memory, so it will be redundant type of memory operations. So if we contrast that with optimized flow where device provides the hint, the entire sequence will be serviced out of the cache. There will be no memory transaction, and again, reduction of memory and system interconnect bandwidth and power. In the backup section of the material that was provided, you'll actually find more details on the semantics of the hints and more details. I was just trying to show in a very simple way the flows of data. Now the next thing that we enhanced the third generation of PCI Express is called atomic operations. Essentially, mechanism for synchronization, although existed in original PCI and was provided in the form of the bus lock, it was removed at some point because of the number of problems and deadlocks that were happening in the systems, mainly due to problematic implementations. So PCI I/O architecture for a while didn't have really way for I/O to, in interlocked way, through hardware means, generate read, modify, write atomic operations to synchronize operations with the host CPU. So we put this back on the table and define the atomic read, modify, write. This type of the semantics and operation that are being defined actually would rely on the rich library of the proven algorithms that already exist, because the read, modify, write type of operations are available on the CPUs, at least on x86 architecture in a kind of a mainstream way. I think I'm not going to read the details, but number of different reasons why we or usages for read, modify, write, low overhead critical sections. In a lot of cases, the I/O and was communicating through CPU with processes running on a CPU using interrupts. You know that interrupts could be very expensive in the current systems, and they incurs a very large overhead. In some cases, operating system will just intercept the interrupt, enqueue the interrupt, and it would be many microseconds before they respond to interrupt. So it was slow and a lot of overhead. And using the atomic operations for synchronization mechanism instead of interrupts actually could reduce the overhead quite a bit. There's a set of emerging applications that will benefit from this atomic read, modify, write. Example would be multiple graphics cards or multiple, let's say, GPUs, where you have now a mechanism for them to coordinate the work in a way and actually share the workload. There's a white paper. I have a pointer at the end that you may, if you're interested in more details, you can take a look, and that may give you a little bit more information on some of these features that are provided mainly to support emerging accelerator applications for PCI Express. This shows the mechanics of how the atomic read, modify, write operation occurs. The device issues the operation. Then there's notion of the conceptual atomic completer engine, which will take the operation, and operation would define what specific type of command needs to be executed, either fetch, add, swap, or cast. We actually had a dozen of operation at the beginning of consideration and distilled to just a bare bone essential, so to make it very simple. So the completer engine will read the initial value, will perform the computation based on type of the command, write the new value, and return the original value to the device. So that's how the device could actually implement semaphores like beat, test, and set, and some of the operations. Power management enhancements. There's obviously energy and performance efficiency is the very important in coming applications. So we developed three major sets of extensions to support better power management. One is called dynamic power allocation. PCI Express and PCI SIG define form factor that allow even adding card that can consume up to 300 watts. Okay, that's very high performance GPU or graphics card. However, I mean, that was the driving motivation, and people have been building some of the server cards that do use 100 watts and more. So obviously the system OEM has a challenge to, provide a power delivery and cooling thermal solution that will, be able to deal with the worst case scenario. However, in a lot of cases, you don't have a situation with the multiple cards where all of the cards consume all of the maximum power all of the time. You cannot assume that they will not consume, so you need to have a mechanism to precisely allocate the power that could be consumed as a budget, as a resource in a platform. So this mechanism actually allows treating the power, both in terms of power delivery and in terms of thermals, as a resource that can be used in the platform, and defines new power management state, active power management state, for who is familiar, is called D0. So we define D0 substates, up to 32 substates that are supported that in a way would allow, under control of the software, the power resource to be managed in a platform. In other words, you can have a 300-watt card that will have that could operate at 150, 200, 50, and number of different steps. Those will be all considered active states. Not all applications could run at all of the power levels, but I think the challenge, besides the plumbing that we put currently in the spec, will be how to support that in a software. And I believe that first ones who will come to explore the benefit of that would be more of the embedded guys and some system vendors that do their own both hardware and software design. Mainstream OSs, Linuxes, and Windows, it may take a little bit longer time, but Microsoft and I think Linux community are motivated to support this capability in the software. Next one is latency tolerance reporting. The problem today is that power management policies and mechanisms, usually they make guesses on what the devices are requiring in a platform, and they try to power manage the devices when it's really not convenient, and that could create from performance issues to even in some cases functional issues. The result of that is typically in shrink wrap OSs, you will find out that most of these power management policies are tuned down and not really being used, meaning you don't get the power efficiency. And the reason is, it's really the power management algorithm is not tuned. There's no information from the I/O device. So we try to fix that by providing something called latency tolerance reporting mechanism, where device will, through a message, will explicitly tell to the power management entity controller in a platform in what kind of operational state it is and how much of latency it can tolerate, and that information would be coalesced among from the multiple devices by the power management controller, and power management controller will set up the policy for the platform, and it will be dynamic. Again, something that is feature that needs to be exploited by the by the software, and but the basic plumbing is there. A number of these features, just to make sure, don't get me wrong, we in a PCI Express community, we believe first that we need to provide some hardware infrastructure plumbing before the software can come, because otherwise it's a chicken and egg situation. And sometimes we ship the products with a hardware support where there's no software, but software eventually comes along. The other one is the optimized buffer flush fill. The first problem is system didn't know about the device operation. The other problem, this problem is device doesn't know what the system activity is, and meaning power management controller, the CPU may be in a sleep state, this new pot may be closed, even the memory subsystem might be shut down. So idea with this one is to provide information from the system to the device in what state the system is, so that device could say, well, let me not bother the system now, let me try to coalesce as many as practical requests over some time, and then create the, in essence, rather than spreading the traffic, creating the windows of opportunity where we can explore the power management opportunity. And that is done using the either sideband signal called wake or using the in-band messaging constructs. This actually feature would redefine the wake that was usually from the device driven to the system. In this case, since it's open drain type of signal, it will be both, depending on the context, it will be platform telling to the devices what the platform state is, and devices also requiring attention from the system. Other protocol enhancements, just briefly touch these. Transaction ordering. In PCI Express, we have strong ordering requirements. Transaction from different requesters are typically not related. Device, this device, when it generates the traffic to the host, and this device, they may not really have any ordering relationship. And reading the either root complex or switches in a more complex topology, like here, there might be strong ordering might be imposed, and that may actually not allow us to take some advantages. So we decided actually to provide the permission for these entities to optimize the traffic flows by treating transactions from different requesters as essentially non-ordered. I/O page fault mechanism. Virtualization is the emerging trend in terms of the platforms. With virtualization, you may have multiple copies of the operating systems, even single copy of operating system. When you need to pin the pages for the I/O, creates the increased pressure on the memory, and with virtualization, that just kind of explodes. So we decided to build on the top of the address translation services that is also known as I/O virtualization, IUV support mechanisms in PCI Express. We decided to extend that with a capability of not only translating the addresses of the pages, but also identifying which pages are present, which are not. So in other words, you're basically providing the fundamental I/O page fault mechanism. My expectation is that the OSVs that are strongly driving the virtualization, they will be the first one to obviously implement this capability. Resizable bar and multicast, this is my last really technical slide. This one is trying to deal with some limitation on the resource provisioning. Today, graphics card and GPUs, they may implement multiple gigabytes of memory, but due to the limitations of the operating system, only small portion could be exposed, and depending on operating system configuration, it could be more or less. But so basically, they go with the lowest common denominator. In that case, that compromise the performance. So this is the mechanism to allow more flexible way of managing the how much of the local memory will be seen by the system. A multicast came from the embedded and communication, but I think we found very good usage model with multiple cards, like multiple GPUs and graphics cards. And in a backup, there's more details on both of these features. Just to quickly summarize, 8 gigatransfers per second is, in terms of being the third generation Gen 3 PCI Express signaling, is still challenging, but we believe it's achievable. We will be essentially doubling the bandwidth without doubling the operational frequencies. There are a number of protocol extensions that I mentioned here that was really just a kind of brief glance just to give you illustration. And as far as the status of the spec, 05 has been delivered. 07 is coming very soon, and you'll see some solid spec that is will be ready for prime implementation starting next year. And you know, if you're in this space, you know, feel free to contribute to the PCI Express evolution. I mean, the best place is the you know, PCI SIG. You can find more information, and these are two links. That's all what I had. I don't know if there's time for questions, but I apologize, I ran a little bit over time.
We do have time for 1 or 2 questions.
Skin Chen from Rambus. So I can see why you are capped at 8 gigabit. Basically, the physics is there. I mean, beyond that. But what does that mean by PCI 4? I mean, are you done on PCI 3 and eventually go parallel or something?
No, I think we still there's a room. So 4th generation of PCI Express. We'll be looking from 12 to 16 giga transfers per second, and also there might be an optical profile. I think eventually all of these interconnect technologies will go towards the optical on the high end. If you look from the system point of view, the high integration will drive a lot of so-called client type of silicon to be a single piece of silicon. And in that case, if you look today, PCI Express or very high bandwidth wide PCI Express is primarily used in a client for graphics attachment. We believe that there will be sort of integration for the mainstream that will pretty much client will be you know, okay with you know, with high integrated solution will be okay with prior generations of PCI Express, mainly to connect to the radios, Wi-Fi radios, and that sort of peripherals.
But what you're saying, PCI 4, you are no longer limited to low-cost HVM, like FR4, that
well,
type of stuff.
I would say this is just entirely speculation or preliminary. I think naturally we will try to identify what is the next generation, what are the limits, right? If 10 gig transfers per second was difficult in 2009, 2010, then well, first let's put this into context. The Gen 4 would probably be, again, take 3 to 4 years time frame. So we're talking about 2014, 2015, let's say, in terms of products being deployed. I think you know, we'll see that at that time frame, can we deliver 16 giga transfers per second, which is twice of 8? I think it will be very challenging. And if we would need to break the backwards compatibility in terms of the connectors and that sort of stuff, that might be a decision that we will need to make. We made transition back when we switched from PCI, PCIX to PCI Express, and that transition was managed, I think, reasonably well. We provided the bridging components. When it is a Gen 4 transition time, it's too early to tell. So.
Okay, thank you.
Yeah. Okay, thank you very much, Jasmin. That was great. Actually, don't go too far. These first 3 seats closest to me. If we can get Bob and Jose to come back up. Sit in the first 3. I'll sit here. So hopefully you found that to be pretty interesting. You know, there's different uses of these interconnect technologies, but there's clearly some overlap as well. Also, hopefully you've developed some questions that you might think that will help provoke a little more information flow from the speakers. And if so, please do line up at the speakers, at the microphones. I see nobody's lining up, so I'll take this opportunity to offer a first question. You know, I think it came out in each of your talks, but it's interesting to think about and perhaps hear your opinion about how these interconnects, either today or in the future, affect the programming model itself. You know, programming is at a point of critical complexity, I think, and you know, there are issues with the current model, but also as we extend these protocols, we could worsen or better these issues. I wonder if any of you guys had a comment about the programming, exposing any of these technologies to the program, all the way up to the programming model.
Okay, let me start. It looks like, does it work? Okay, now it works. Well, it depends on what you consider as the starting point. I mean, if you consider that in the past we had single core processors, if you compare with that, then things are going to become more complex, because as we add more cores, then things will become more complex in the sense that at this point in time, for instance, consider a processor today, an x86, it doesn't matter whether it's Intel or AMD, contains a few cores inside. In the future, it will likely contain many more cores. But the question is whether those cores will be interconnected in the same way they are connected today, or they will be connected in a different way. And it's very likely that they will be connected in a different way. And there will be opportunities for things like, for instance, instead of increasing the number of cores in a single die, you may go for multiple dies inside the same package. And that will shorten time to market and design complexity, and therefore design cost, and will be more cost effective for both the customer and the company. So that means that there will be multiple levels, not only an on-chip interconnect, network on chip, but also on substrate. And possibly technologies like QuickPath or HyperTransport will move into the package as well. So in doing so, you are increasing the number of different layers in the hierarchy, and therefore the different latencies that will appear in the system. So that in fact makes programming models more complex. Because the naive programming model in which, okay, you consider a cache coherent shared memory platform where all the latency is exactly identical, that's fine. But when you move into those future systems, you will realize that even if you manage to keep all the system cache coherent with shared memory, latencies will have some hierarchy. And depending on how you manage to exploit locality, the performance would or could be dramatically different. So this is one aspect of the future reality. Even if you manage to have a simpler programming model, in practice it may become more complex because of those different latencies, and therefore the need for managing locality. The other issue is that if you compare with current clusters are relatively complex. People are becoming less and less happy with them, simply because there is, again, mixed kind of models where you have message passing among different motherboards and share memory with cache coherent within the motherboard. It would be nice if we could manage to scale cache coherent share memory to very large sizes, say tens of thousands of nodes. But nobody knows the solution. Nobody has architected any solution for that, so that cache coherent share memory could scale to those sizes. So what do? Either we keep with the same model as today, mixing message passing and cache coherent shared memory, which people are becoming less and less happy with it, or we move to an intermediate programming model, which is basically shared memory with a global address space, but not necessarily coherent. Where you will have shared memory, you will have the benefits of shared memory, but you will have to explicitly move data in and out so as to first exploit locality, and second, keep data you are going to handle more frequently within your closest coherent domain. So that will increase the complexity of the programming models by adding one more layer, possibly removing message passing in the long term, but in the meantime, adding the complexity of handling data. That will increase the complexity of programming, but hopefully that will allow for better modularity, flexibility, resource utilization, and people will value that, and sooner or later will develop support for those programs.
That's the intent of the high node count stuff you mentioned.
But you also have to take into a few accounts as software legacy is not going to go away.
No.
No one rewrites the bootloader as an example of legacy you wish would go away. If you look at the code that's in there. Not that I have an opinion about that. But you look at those kind of things, and so the consistency model there is, for lack of a better term, you're shackling us to a certain degree. There are going to be other areas that we are overly constrained that we do have opportunities to take advantage of. Jasmin pointed out one where basically we have multiple streams of PCIe data basically flowing up. Well, at that serialization point, you've lost identity of which stream goes to which stream, and so basically the serialization point basically has to assume producer-consumer model that all transactions are related and therefore order them restrictively, safely. If that information is basically, if knowledge of the streams are carried forward, basically all of a sudden the overall performance of the system is now allowed to expand without changing a single thing. That would be a huge step, and we don't even change the consistency model. Also, the areas of getting the data closest to the consumer is also another area that, again, without changing the consistency model, will help a great deal. So even in the restrictions that we currently have today, there's still plenty of room for improvement and innovation within the next 2 or 3 years.
Jasmin,
yeah, I would like to add a comment from the I/O perspective. When you look at the I/O interconnects today, the basic software model that is assumed is device driver model. So peripheral is seen through the device driver, including the graphics. Over time, we got with some more advanced API, DirectX, for example, in a Windows. We see the need based on emerging applications and capabilities of the GPU hardware that is still attached to the I/O, to come up with the APIs that will actually allow more direct access to the hardware, but with still some level of abstraction. So that's kind of beyond device driver model, and I think you guys will be hearing today in OpenCL. It's actually to bring the I/O to a more equal citizen, and in some cases you may have something that resides on the I/O interconnect, but is really a partner in a collaborated processing environment, and maybe to offload some specialized functions. So the device driver model that we have today is fairly restrictive, and things are happening in industry today that will move it to the next level.
Yeah, that's an excellent point.
And I think the key thing is the standardization, right? Because without standards, everybody could implement their own, but a large set of applications would not be built ever if there's no common layer.
Oh, good. Thank you. Those are all excellent points. Yes, there's a question over here.
Yes, Doug Derfler, Sandia National Labs. So we did hear a little bit about the data integrity of QPI and error detection and correction, but didn't hear much from HyperTransport or PCI Express. So could you maybe say a few words about what you're doing now and what you think you'll have to do in the future, and if there's any as the bit rate keeps getting higher and higher, will a CRC8 still be sufficient, or are you going to have to do more?
Yeah, well, I didn't mention details, but there is also support for CRC in HyperTransport, obviously, because we are running basically the same clock frequency at the same link width. So features are slightly different, maybe a little bit less reliable in the sense that we don't provide that support at the fleet level. It's a bit, it's on the per packet level, but it's still efficient enough so that current systems are running and don't fail too frequently, as you can observe.
I can answer for PCI Express. We have a fairly robust data integrity 32-bit CRC for the packet level protection for the transaction layer packets. That's a link level, you know. On the top of that, we have additional 32-bit CRC for the end-to-end that will basically guarantee that no information could be manipulated or compromised throughout the hierarchy, meaning when the traffic flows through the switches. Because if you support a link local data integrity, that's not good enough. You leave the problem to somebody else who will develop these fabric components to implement that. On the top of that, we have a robust RAS capability that has a software programming model so that you can find the errors, you can isolate them, and potentially isolate the bad links and potentially reconfigure in the future. So that saying, with the Gen 3, it's actually data integrity gets even better. I'm not sure if you were able to grasp a little bit of, but that the framing mechanism, that's actually it's actually improving the data integrity.
Okay, thank you.
It's Ken Chen from Rumpus. So I kind of just wonder, so with the power constraint, and most of you actually have power management, but in reality, I'm looking for like next generation speed. How did you guys decide the speed? I actually asked a question on PCI Express. In reality, the speed strongly depends on process. And we all know kind of process kind of slowing down further and further. So, I mean, not further, I mean in the progressive scale. So do you guys see still 2x like 2x speed increase from generation to generation, or should we just look at the process and define the speed accordingly so we can get the power optimized like interface design? Does that make sense, the question? My question is, maybe at some point doesn't even make sense to continue to do 2x spec.
All companies and all interconnects are going to push the envelope as far as they can go. That's without saying. But I think in reality, the real question is, when you look at like computer rooms, basically, if you look at, they can only bring in so much power, and they can only output so much heat. We all have a serious problem here, and you heard we had adding the device extensions to managing power. We heard both of us mention things about power management. The system platform is what we have done really at the CPU level, or at the core level, basically is going to expand into the platform level. And basically, the best way to think about it this way, given the fact that we are working always in a finite power envelope, is power used wisely equals performance, power used unwisely equals heat. And everybody wants us to be more on that first line, not the second.
Yeah, that actually precisely what I'm saying, but I'm saying, do you guys see still kind of, like for instance, QPI will go to 12.8 at all, or each will stay at 6.4, or next generation become 8 instead of 12.8?
For the most part, cores get faster. And I don't mean necessarily by definition of frequency. They get faster by, they can consume data more efficiently and actually produce data more efficiently. Ultimately, we have to get the data in and out. However we do that, would be going faster, moving it better without copying it a number of times, all come into play here. I think there will be a slowing of the data transfer rates to a certain degree, but will they stay at 6.4? No.
Okay.
Yep. An observation that I agree on that power management is extremely important, but just want to mention that if you look at how processors will likely evolve, they will likely incorporate many more cores. They will reach a point where not only power, but also memory bandwidth will limit performance. And that will be the next wall, for sure. And that memory wall will need to be addressed. there are ways to increase bandwidth across the pins, including optical technology. But those are quite esoteric and quite expensive. And the solution would likely be to incorporate 3D stacks of DRAM inside the package. Not in the same chip, multiple dies. So 3D stack of DRAM dies next to some multi-core die or multiple multi-core dies. Okay, so that will likely be the solution. But in doing so, you will keep increasing the number of cores and the amount of memory within that package. And that means higher needs for bandwidth in order to interconnect the multiple chips that will be in the system. Because now it's not only accessing the cores, but also accessing memory inside those packages. So I would say that in general, an interconnect should be fast enough so that it doesn't introduce congestion and therefore slows down the entire system. As long as it doesn't slow down the entire system, that's fine. So the perspectives are that we'll have more cores inside the chip, we'll likely have significant amount of DRAM inside the same package, and therefore the needs for higher bandwidth will continue to increase.
Okay, I believe you were up first.
Oh. Well, thank you. I'm John Delaney, and I'm concerned that I'm a little confused about something. It appears that QuickPath has 6.4 gigatransfers per second and a total bandwidth of 25.6 gigabytes per second. Mm-hmm. And PCI Express 3.0 has 8 megatransfers and 32 gigabytes per second. Is there a problem here?
PCI Express Gen 3 has the target rate of 8 gigatransfers per second. That will translate into the raw bandwidth that I quoted, 32 gigabytes per second. You know, how much of that is realizable bandwidth? That will really depend on the system. We didn't want a PCI Express to be the bottleneck of the I/O performance, right? The performance would be limited, obviously, with the memory. You know, even if you have the best of the breed system interconnect like HyperTransport or QPI, I think we will be still fundamentally limited with the memory. And as Jose pointed, some of the cache or memory hierarchy will be redrawn over time. Maybe there will be more and more integration of the memory on a die, because I think the current rate at DDR, you know, how many channels of DDR3 or DDR4 you can put in the future on one chip, not too many. That is not very scalable. So I'm not sure if I'm addressing your question, if the question was concerned between the gap between the two, you know, why the I/O is higher. What you heard from Bob is the, maybe to put fine line, is the first generation of the QPI. Obviously, QPI is highly scalable as well, and we'll go through the transitions. We don't want to comment on the products we're not ready to announce. I'm speaking on behalf of Intel. So besides 6.4, you know, you'll see higher rates in the future. Oh, and PCI Express is a public, it's a SIG, so I could say in that case. Otherwise, I wouldn't even say anything about Gen 3.
So my follow-on question is, if I understood this correctly, PCI Express 3.0 has double bit error correction and triple bit error detection. Right. And if that's true, and QPI has triple bit error correction, so that sort of implies that the links they're using are not as good as the links you're using. Could you explain some of the assumptions you're making?
Right. Well, it's probably, Bob can comment, but I think it's the question of the controllable environment, right? The one thing is the system interconnect, where you tightly control, and it's not like 300, 500 adding card vendors like in a PCI SIG environment, PCI Express ecosystem, where you have everybody from, you know, the manufacturers that need to deal with high volume manufacturing. So some of the, you know, robustness that we, and conservatism that we build in a industry standard technology is it's necessary as a insurance policy. I think with a more tightly controlled interfaces, we could probably live with less, because it's usually the complexity and overhead.
Well, I guess the problem is that the higher speed link has less ACC, and that's a strange thing in the world.
Yeah, we'll let that comment sit for now. If you'd like to talk about it offline with the speakers, that would be okay. We got time for, I think, one more question or two quick ones.
I'm not sure what misunderstanding is.
So I think I'm not sure if you said ECC, but it's a
CRC
CRC protected, so that probably maybe misunderstanding.
Yeah, I have a feeling there's a couple entanglements in there.
Yes. Yeah, thank you. This is Songjin Chen from Apple. So the chairperson began this discussion by commenting on the overlapness of the three approaches. And I think this is especially so between HT and QPI. So I would like the speakers who speak on each of these two topics to contrast your approach versus the other. In other words, for what particular market or application, it's better addressed by your approach, QPI, for example, versus HT. I mean, going through this, I can't help but just say, hey, they are more or less two different standards trying to address the same market, same application, more or less, big overlap, championed by two different CPU companies.
Yeah, I'm going to intercept that question. These guys are up here to really explain the technology, not to provide the marketing perspective on where they go into the specific products. In fact, the HT spokesman isn't even representing a product company. So actually, you're free to ask that question offline to the guys, but I don't want them to answer it here.
All right.
Sorry about that. Final question.
Yes, could you comment on the use of these interconnects as a means to ease the inter-motherboard traffic if you want to build larger systems by interconnecting motherboards, particularly things like PCI Express, that are things that would be very nice to do, but that are hard to do today because of the root complex requirements and so on. And I'm not sure whether that's being addressed in the next specs.
I guess the question was related to PCI Express, how it can be used to remove some of these interconnect challenges. PCI Express is fundamentally I/O interconnect technology. It can be used for reading the blade systems for both I/O and perhaps tunneling of some of the protocols, even the IPC, interprocessor communications. You will see people using it already. There's specifications under development still, multi-root IOV. It's started primarily as a device sharing technology for virtualization, but basically what you can see is the multiple CPU boards connected through PCI Express, where PCI Express could be used as interprocessor communication mechanism. Some people will take that as a reading, okay, if I'm talking board to board, I don't necessarily need to go through expensive, high latency network, LAN type of infrastructure, and I can connect directly through more, much leaner, lower latency links, and and then depending if you need cache coherency, is that going to be HyperTransport / QPI or PCI Express or some derivatives? I wouldn't comment again on the future technologies, but I would say that for the PCI SIG, the multi-root I/O virtualization or multi-root IOV is the technology that will enable some of these blade tighter, clustering within the chassis. Intent is not to go between the chassis, although once when we go into the cabling, and there's a cable spec as well, once when we go into the cabling and in future in potentially optical, the physical span of the interconnect would be increased,
Yeah, just one short comment on this. Please check a product called NumaScale. NumaScale provides support for, well, not sure that it's scalable, but it provides support for up to 4K nodes with cache coherent shared memory, and the physical layer is PCI Express.
Now, I was a little confused in your question. Did you mean, because when you first started asking your question, were you talking about the ease of routing of motherboards and things like that? Because you started off with that statement.
Well, there are limitations in the way that these interconnects are structured that make it difficult to use them for these low latency inter-motherboard connects, right?
That's true.
You know, it actually is interesting to contemplate what could be done to make that job easier. I mean, some of the distance limitations with the HyperTransport or QPI, that may be difficult to do. PCI Express probably has more of a chance, but.
Well, I think if the question is, can you bridge the gap between the interconnect lengths? There will be technologies that could allow you longer channel length, and when we go into the optical space, you know, then we will be really more limited by the usage model. I mean, you know, in some cases latency as well, because the information will travel at the speed of light as it is today as well. And can you put PCI Express fundamentally to go through an optical link across the kilometer? Yeah, maybe feasible, but you know, it wouldn't work for the application where the usage model expect some reasonable latency, because a lot of architectural elements, flow control and all of that stuff is built on the premise that this is very relatively short distance. I mean, short time length in a sense. But short number of nanoseconds. But
still, all three definitions basically are defined hierarchically in nature, and if there's a better signaling, whatever that is, whether not be on copper or whatever, people keep trying to use the word optical and stuff. If there's a change, ultimately the higher levels, the higher levels can sit on anything. In fact, I'm sure you can take RS-232 and put QPI or HyperTransport. I don't know if you ever would want to, but you could. I mean, you can put things on a cable. So, I mean, since with link-based definitions and defined hierarchically, then basically as things change, you can change the layers without changing the overall picture. And if there is a cable-based solution out there that provides a good interconnect or whatever, then that it can be easily. It can be you can provide a cut line to define an interface that can utilize that physical interface.
Yeah, but to certain point, because as Bob mentioned before, there is the need for flow control. If your higher layers require flow control, then it's a problem, because link utilization could drop to very low levels, and nobody wants that.
Right, but it functionally works.
Functionally works.
Functionally works. It's a utilization.
As long as you use credit-based flow control, whatever you call it, coupon-based, whatever, but as long as you use credit-based flow control, even with small buffers, you keep increasing the link length and it will work correctly, but not efficiently.
So just to make it clear, none of these three technologies are essentially networking technologies. You'll still see, and there's still huge value for evolution of Ethernet. You'll see 40 gigi and 100 gigi. Those will be unreplaceable in most of the application. The question is on a short haul, you know, communication, reading the cabinet, and so, I mean, do you use the 40 gigi, or do you use something else that is maybe PCI Express derivative or 100 gigi?
So stay tuned on that. I think we'll be hearing more about that kind of system topology in the upcoming years. Well, there's lunch for 250 people sitting out in that grove out there. So at this point, let's thank the speakers one more time and conclude the session.